Hello, everybody. My name is Andrea Malchiodi, and I'm currently the director of the Giorgi's Mathematical Research Center. I will just say a few words, and I promise I won't take much of your time. The center is named after the outstanding mathematician Ennio De Giorgi, one of the most prominent figures of the last century. It was founded about 20 years ago formally as a research lab of Scuola Normale Superiore, but with the mission of being a center for the whole mathematical community in Pisa, which includes colleagues from the university and from Scuola Superiore Sant'Anna. These institutions, in fact, both contribute financially and crucially to the activities of the center. The main activities since the foundation have been workshops, schools, and intensive research periods. The center has visiting position of two types, 2 years postdoctoral positions, as well as a visiting position of short time to perform research in pairs. So as many of the centers of this type, the activities in the past 2 years were strongly affected by the pandemic. We had in the fall some in-presence events after a long break, but we have to unfortunately switch this one online given the circumstances. I hope in the spring I will be able to resume the workshops in presence again. So I take the opportunity to thank the organizers for having brought up this really high quality event, and especially the staff of the center to make it possible. So it is extremely difficult to plan activities in these times due to the continuous change of expectations from people and regulations. Well, I'm basically done, and we're having next a short video with an institutional greeting from Luigi Ambrosio, the director of Scuola Normale Superiore.
Good morning. I'm welcome to this meeting on transport fluids mixing. I'm sorry that, of course, it would have been much better if this meeting could take place in Pisa physically. I see in the list many former students of mine, many colleagues with whom I collaborated in the past, also many younger participants, which I still don't know. And anyhow, I think the program seems very exciting, and I wish you all the best for this meeting, hoping that maybe in the near future there will be another occasion to be in Pisa. The Centro de Giorgi might restart its usual activity and so on. And of course, I had to say I'm very busy in these days as a director of the Scuola, but I will try to attend a few lectures. And so have a nice meeting and all the best.
Okay, so thank you, Andrea, and thank you, Luigi, indirectly. So maybe I also say a couple of words on behalf of all organizers. So first, I thank my co-organizers, so Laura Spinolo, Stefano Spirito, Giovanni Alberti, and Anna Mazzucato for all the work in the background. And of course, I would have loved to welcome you in presence. I mean, from Aula Dini in Pisa. So this would have been wonderful in several senses. So for me, it would have been an occasion also to come back to Pisa. So I'm not there since quite a bit. We would have enjoyed great coffee breaks in several senses. So not just coffee and pastry, but also talking together, which I think is something we're missing a lot in this time. So meeting colleagues and get, all the good things from this random casual conversations. But okay, I think this online forum is at least a way to go on with our activity and to keep ourselves in contact and keep up to date with our research. So although it's not the same as being together at the place, I think there is again quite a big value in an online workshop. So I also want to thank the Centro de Giorgi for all the help in the organization of the activity. So on the one hand, for the support and for the possibility of organizing this workshop, but also the technical staff. In particular, he had a lot to do with Sabrina, who is there. And as Andrea was already mentioning, so it's very complicated to organize something which is first supposed to happen physically, and then there is all the physical part of the organization, so hotels, budgeting and whatsoever, and then it becomes hybrid, and then it becomes online. So it's like organizing 2 workshops, and I'm very grateful for that. And we also had to acknowledge, in a sense, financial support from the Centro de Giorgi, from the European Research Council, through the FLIRT starting grant, the University of Basel, and the Prima project around Giovanni Alberti. And okay, so these funds are no longer required, but I think it's you know, we're still glad to acknowledge this potential funding in a certain sense. So that's basically all from my side. So in a while we start with the scientific activity. So just a note about, maybe a technical note about the schedule. So we have, you know, we try to occupy all the afternoons with the idea that we have a lot of participants who are US based. So we try to maximize the times which are good for both the Europeans and the Americans. So we start every afternoon at 2 p.m. and we go a little bit like in the evening until 6:30. We also have 2 mornings, so Tuesday, Thursday. So we have 10 to 12 with two talks each morning, each of these 2 mornings, so Tuesday, Thursday. Nevertheless, we will have recordings. So there will be some provisional recordings. You will get, I guess, at the end of each day, a link with you know, some instruction how to download these recordings. So this is particularly relevant for participants on another time zone, so they can say keep up to date. And then there will be a post-processing of the recording, and in some time, I guess a couple of weeks, they will be available for everybody in the final form on the website of the center. So the Zoom link will be active for the entire week, so there will not be a new link every day, so it's just going to be the same. And I think that's everything also from the practical point of view. I hope I'm not missing anything. Then I think we can start with our afternoon. So we are very happy to have here Franco Flandoli. So good to see you. And so you are doing an iPad talk. You're sharing slides.
Yes.
Fantastic. So I would start at 2, so on time, but maybe you can already try and share your screen or. Okay, so I see that it's 2 p.m. now. So I'm very happy to introduce Franco Flandoli from Scuola Normale Superiore di Pisa. So we start very local. So you want, I guess, the participants in physical presence. I assume you're in Pisa. And Franco is going to talk about small-scale noise in fluids. So please.
Thank you very much, Gianluca, and the organizers and the Centro de Giorgi. I'm very happy to give this talk. It is in 2 parts, divided in 2 parts. The first one will be a sort of general introduction with historical comments on the Navier-Stokes equation with noise, especially from the viewpoint of the attempt to prove some special theorem of well-posedness that unfortunately failed in a strict sense until now, but there were progresses. And the last part, if I have time, I want to give some technical details on the last paper that with Dejun Luo we wrote on this subject relatively recently. And so there is behind the story this reference problem open. I never touched this problem in itself, so it must be clear that I'm not going to speak about the open problem of the deterministic 3-dimensional Navier-Stokes. Anyway, please remind that it is composed, so to speak, of 2 questions. One is the uniqueness of weak solutions. In fact, uniqueness of Leray weak solutions. Otherwise, in a sense, this would be weaker than Leray would be solved today. And the other side of the question is the global existence of smooth solutions. I wrote the first equation you see here. I wrote this equation in velocity and pressure, the classical formulation, the Newtonian classical formulation of the Navier-Stokes, and this second one is written for the vorticity, the curl of the velocity, which is maybe interesting for the regularity of solution, for the attempt to prove a global existence of smooth solutions. Smooth means could just mean L2 solutions from the viewpoint of the vorticity. And the difficulty is mainly in this term that will appear later, also in the stochastic case. And for some time, a number of us, me and colleagues, were attracted by the corresponding stochastic problem. So the problem whether the addition of a noise may improve the theory of this equation from the viewpoint of uniqueness of weak solutions. First, this notation W prime means the distributional derivative of a Brownian motion. The Brownian motion is W and is a Brownian motion which depends on time and on space. And the reason why, I mean, there were maybe many reasons, but basically one of the reasons was that if instead of a difficult PDE like Navier-Stokes, we consider this simple ordinary differential equation in finite and Euclidean space, then an additive noise has an extreme power of regularization. It regularizes nonlinearities which are just bounded measurable. Even some distributional drift can be accepted. And so it's really a very general phenomenon. And therefore, it was extremely natural to try the same for infinite dimension, for PDEs, in particular for the PDEs that have outstanding problems of the uniqueness. In the case of Navier-Stokes is a question. It's not that there is no uniqueness, but it's an open question. And let me mention only, without writing any result, that many people, Marco Romita, that is in the audience, was my main collaborator in this adventure. We tried to prove something. We reached this result. This was the best result that we reached. Namely, it is possible to, thanks to the noise, it is possible to make a selection of solutions. For every initial condition, there are at least one. So a selection which is Markov, but in particular, it has a continuous dependence on the initial condition globally in time. Locally in time, it is known that one can construct solutions that are continuous with the continuous dependence on initial condition. But globally in time, it is not known in the deterministic case. And in the stochastic, it is true, thanks to the Markov property and other properties that I don't want to discuss. There were also the result of the technique of finite dimension that I mentioned before was also investigated in infinite dimensions, and we wrote, people wrote several papers of generalization, but they don't approach Navier-Stokes. So at the end of the story, this approach to uniqueness is open, and in a sense, it is difficult also to have a conjecture and have a path to approach this problem, because we tried Kolmogorov, of course, Girsanov, but that was left. I mean, we tried many things, and there is a problem even of ideas now. Around 2010, there was a change of paradigm. Because we realized that instead of using an additive noise, you remember let me go just 2 slides before. The noise was always additive, namely simply we add the noise like a forcing term. Instead of doing that, around 2010, we started to investigate strongly. It was not the first time that it was done, but we started to investigate very deeply what happens when the noise appears in this particular form, transport. There is this funny notation of the circle in the middle because it is the Stratonovich meaning of the multiplication it's necessary from the stochastic viewpoint to distinguish between Stratonovich and Ito, and the Stratonovich is the correct one. But if you want, now at this level of the talk is a detail. And the first result that, in a sense, marked starting of new theory is this one with Massimiliano Gubinelli and Enrico Priola, in which we extended, so to speak, the theory of transport equation with weak drift, but weak in the deterministic case essentially means weakly differentiable, roughly speaking. Here it was extended, in this particular paper, it was extended to Hölder drift of any order up to assumption of the divergence. And we got the uniqueness of weak bounded solutions. And later on, this was extended to several other classes of regularity, other generalization. Let me also mention that it was extended to vector valued problems. Linear, always linear. Namely, in the linear case, there are several approaches now understood, and they work very well. And the noise, in the linear case, the noise is just time dependent. One can take a space dependent, but it's not necessary. Just a time dependent noise has this power of regularization for linear problems. When we go to nonlinear, the situation is completely different. This noise, so simple, just time dependent, doesn't work. There are immediately counterexamples exactly for the equations of fluid dynamics, like Euler two-dimensional Euler equation. Also, some people got results with Massimiliano and Enrico. We treated the two-dimensional Euler equation in the particular case of finite number of point vortices, and this point vortices, this distributional object is a weak solution of the two-dimensional equation written here with the noise written in this transport way. And the result is that these points, vortices, they don't collapse. Opposite to what happens in the deterministic case. There are explicit examples of collapse of point vortices. And with François Delerue and Dario Vincenzi, we extended, so to speak, but improved also the result in the case of the one-dimensional Lazo-Poisson problem, in which point vortices are replaced by point charges. For PDEs, there is a result on by Barbato, Bessai, and Ferrario on the Leray alpha model, and others with Barbato and Morandin, and also Luigi and Mediobianchi, another paper on the dyadic models. So in all cases, the noise has a very rich space structure in order to create this particular regularization phenomenon. Okay, this slide is just to say that regularization by noise now became a topic in the mathematical classification. So if you write a paper, you can click, you can put this link, and this is I mean, there are many more people that contributed, and I put the names without an order, so you cannot find your name or find that is not your name. There was a breakthrough in 2019 by Lucio Galeatti. In his master thesis, he understood under David Barbato, so there was experience also in that group, they understood a new phenomenon that opened a new possibility of investigation. The phenomenon is this one. Here I wrote again a linear transport equation. This, in fact, was the result of Lucio for the linear transport equation with a noise in transport form. The noise is parameterized by capital N, parameter capital N, which will go to infinity. There is an information that I didn't give before in the talk, that is, when I write a Stratonovich noise, this circle multiplication, rigorously speaking, this means the sum of an Ito term, a classical Ito integration, plus a corrector, the so-called Ito Stratonovich corrector, which, if you take the noise of some form, a suitable form, this corrector is a good second, is always a second order weakly elliptic operator. And this structure of second order operator comes from the fact that is a transport noise, but it can be degenerate. For instance, if W is equal to 0, there is nothing. It can be degenerate, but if you choose the noise carefully, this second order elliptic operator can be even just the Laplacian, or more complicated, strongly elliptic operator. Nevertheless, one should not make the mistake. These two equations are equivalent. And the first one has the explicit formula of representation of solution in terms of initial condition with the inverse flow, with a special stochastic inverse flow. So there is nothing parabolic in these two equations, nothing parabolic. It's just the fact that a Stratonovich integral has a reformulation in which a Laplacian appears. The key result of Lucio was to find a special scaling limit, in which the term, the Ito term goes to zero, and the Laplacian goes to a Laplacian with a strictly positive constant in front. If I should find in the literature analogous results, not analogous in the strict sense, but something that reminds that, for instance, I remember the paper of Schneermann that in order to construct a special solution of Euler equations, he activated in Fourier certain modes, high wave modes, and these modes go to this activation by this additional forcing goes to zero in the weak sense, and there is a trace of that for low modes which does not disappear. Later on, there is the theory of convex integration that maybe from a certain viewpoint can be seen a sort of similarity, that something goes to zero in a weak sense but leaves a trace to the problem which produces a special behavior. And after this result opened the possibility of many consequences, in particular about regularization by noise. With a number of friends and colleagues, we understood several consequences. The first one is of physical relevance, if you want, namely it's an explanation of the concept of eddy dissipation or eddy viscosity. There are also other explanations in the literature, but it's a new explanation of the concept of this concept. I will not speak of that during the talk. Unfortunately, over finite time, so it's not the mixing or dissipation enhancement typically investigated because of the restriction of finite time, but on finite time we have a very quantitative estimates which look like mixing and dissipation enhancement due to this. Because of course, if you have a Laplacian which raises in the equation, of course, this produces this kind of the dissipation, especially it explains the dissipation and also due to the fact that in a sense we have a new Laplacian into the equation, we may prove that the blow up of certain equation is delayed. And I quote here two papers, by the way, some of the authors, Peter Constantin, Peter Heyer, and Latoche are in this conference to them this afternoon. These two papers were really, truly speaking, a really important source of inspiration for our understanding of these questions. I want to explain this dichotomy in order to move then to the three-dimensional Navier-Stokes equation, the dichotomy between exogenous and endogenous action of this transport noise. Namely, until now, I showed the transport equation with this transport noise that is exogenous. Namely, the noise is like a fluid field, random, turbulent, which we put into the equation for a passive quantity, passive scalar or vector field. Endogenous means that we put into the equation of the fluid themselves. I call endogenous because of the intuitive meaning of this noise is fluid, and we put this in a fluid equation. So this endogenous picture requires some kind of justification, some kind of explanation. And so putting together the last slides, there are two questions that we are faced to discuss. The first is what I just mentioned, that when the noise acts on the fluid analytic equation, we have to understand what this sentence means, because we have fluid on fluid, like a fluid divided in two parts with 2 minutes. Where does it come from, this additional noise inside the fluid equation? The second question, related to the previous slides, is can we prove regularization of the fluid equations using this kind of noise? So let me first speak a little bit about the endogenous noise, which could be the motivation. My best understanding today, which certainly is not the final, so maybe only very preliminary, we spent more or less 2 years until now on this topic, but certainly this is much deeper, is the following. Decompose, this is rigorous, is a decomposition of the equation for the vorticity, 3 dimensions, decomposition in 2 parts. I call large scales and small scales, but this is an interpretation, because what is really decomposed a priori is the force and the initial condition. This we can decompose, these are data. Then we write this decomposition, but of course we are not sure that the solution of this system maintains the meaning of large and small scales. At the time 0, yes, by choice. Later, it is not completely clear. This system is equivalent to the original equation, because if you take the sum, is exactly the original equation for the vorticity. Notice here that this u, the u which acts in this position on the vorticity, is the global velocity, is the velocity associated to both parts that let me call large and small scales. Now assume that the small scales can be idealized to be a white noise. Then simply algebraically replace, and we get the endogenous noise in the equation of the fluid equation. So this is why I gave the title of small scales, because when I use this noise in fluid dynamic equations, the best explanation that I have today, which is still very vast explanation, is that it represents small scales in an equation for the large scales. We have a number of results on this kind of decomposition. This is an example of the results written for a two-dimensional problem. So this problem is a two-dimensional Euler equation. Sorry, I noticed now that I used a slightly different notation. I should put a bar over here to be consistent with the previous slide. And the point, the key point is the following one: that following also, for instance, this paper of Maida and collaborators, if we replace, of course, neither Maida nor ourselves, we cannot justify rigorously this replacement. There are intuitive justifications. If we make this replacement, namely we replace the small scales by stochastic dynamics with a special form of activation of the stochastic dynamics, then it is possible to prove what we want, namely that the solution of the large scales, this omega is with the bar above, compared to the previous slide, this large scale converge to the equation, the equation with the transport noise that I wrote. That, rigorously speaking, is the sum of Ito plus the corrector. I want to stress this because sometimes if one starts with Stratonovich and writes that is the sum of Ito plus corrector, it seems magic, and people say, yes, but you put the corrector in the equation from the very beginning, it looks like a trick. No, it is a rigorous theorem. If we start from a problem composed of this equation and this equation, in the scaling limit, we find this model in which there is the corrector, which is a second order elliptic operator. Okay, let me, this slide summarizes the final picture, which unfortunately is mostly heuristic. After the slides, I will explain some technical comments, but probably not all that I prepared. So this slide is very important. The final picture that we got from this 2-3 years of investigation is the following one: that at small scales, presumably, it could be reasonable to have an additive noise. An additive noise, as you see in the previous equation, there is sorry, let me delete something to show that this is an additive noise at small scales. So this resembles the additive noise that was used years ago in the attempt to prove regularization by noise, but in the sense of uniqueness. So at small scales, we have an additive noise which produces in a special scaling limit that the small scales themselves look like a noise. These small scales act on the large scales by advection and become multiplicative. And now the question is about the regularization power of this scheme. Until now, unfortunately, we have only a very partial result with the Jean-Luo that I will explain in the next slides, namely that the transport term contributes to to delay the blow-up of the three-dimensional Navier-Stokes equation. If the other term, unfortunately, spoils this contribution in general, especially it spoils for noise, for the simplest noise. If one takes the simplest from the physical viewpoint, namely the isotropic, for isotropic noise, it spoils the positive contribution due to the transport. The stretching term is very dangerous. However, we are trying to understand if noise with other structure, with more geometric structure, may be less strong from the viewpoint of stretching, especially we investigate the passive magnetic field at present, and I hope that there will be some positive result in the next future, but I will not talk about the passive magnetic field today. And so, at the end, maybe not immediately, but maybe one day it is possible to prove that additive noise regularizes three-dimensional Navier-Stokes, but not through the, let's say, generalization of finite dimensional theory, but through a more complicated picture, which has to do with the cascade and with the interaction between small and large scales of the fluid. Maybe I'm not sure that this is true, that this is possible. In the last 10 minutes, let me say something about this result with the Junluo. In this result, we have only transport. We have to project the transport term on divergence-free field. In the next slide, I will explain why. And for this three-dimensional Navier-Stokes type equation, because it is exactly the three-dimensional Navier-Stokes with a particular noise added, we have this theorem that there exists noise, there exists a large class of noise, which produces no blow-up except with a small probability. The precise statement says that, but for the precise statement has to do also with the size of the initial condition, because is very similar to the statement that large viscosity prevents blow-up. So if you prescribe a size of the initial condition R0 and a small probability parameter epsilon, there exists a noise with the following property, that for every initial condition, small, I mean very large, but smaller than this size R0, the solution is global and unique because it's regular, global and unique up to a probability epsilon. If we denote by tau the maximal time of existence and uniqueness, this maximal time is plus infinity except with probability epsilon. And let me mention that with the Junluo, but also Martina Hoffmann-Nolan and Nielsen, we have proved some variant of this result that I will not discuss. Why the projection? The projection is because if we don't take the projection, if we consider this equation without the projection, the first part of this equation has a divergence 0. And so this, okay, for smooth solutions or in the weak sense. So there is if something is a solution, then for this something also the divergence of the transport term should be 0. But the divergence of the transport term is always non-zero except very particular cases. And so we have to project. That this is a source of technical difficulties. Let me explain some ideas of the problem, about the problem. I prepared too many slides, but I can give the slides to check, to see more. Some ideas are the following. Assume that the noise is written in Fourier in this way. Later I will be more precise, but assume that there is a Fourier formulation of the noise. Then when we pass from Stratonovich to Ito, the corrector is this operator L, which is the iteration of the transport term. So there is the transport iterated, unfortunately iterated with the projection, And so we have to understand this operator, is a negative operator. We have to understand it looks a second order operator because there is a gradient twice, but there are the projection which makes it very complicated. We would like that this operator is similar to a Laplacian. So, so this is the first point. The basic steps of the proof are: the first, understand that this operator looks like a Laplacian in spite of the projections. The second step of the problem is proving that the Ito part goes to zero. You remember Galeati principle, idea is this one, the Ito part goes to zero. And the last step is to put together these ingredients to show that for the equation there is a delay of blow up. So in the next slides, I simply comment on this. The second problem is stochastic analysis. When you know the details of Ito integration, you compute the second moment of the Ito term using infinite dimensional analysis and understand that it goes to zero. The third problem for experts of Navier-Stokes is relatively easy because it's a question of estimates. There is somewhere to use a negative Sobolev norms, but it's really not a problem. So the only mysterious issue in this story is why this second order operator is similar to a Laplacian. And let me say only something on this, Let me say that if instead of the true operator with the projection, we have this simplified operator without the projections, the structure of Laplacian is partially straightforward and partially a complicated exercise with Fourier coefficients, namely, but not so complicated, sorry, because immediately this sum can be rewritten as a second order differential operator putting together the coefficients sigma k. And then the question is to have that this sum of coefficients is equal to the identity matrix in R3, in order that the divergence of Q gradient omega is the Laplacian multiplied by a constant as we like. And this can be achieved by taking classical basis of the space of vector divergence-free vector fields, sine and cosine, with vectors. These A are vectors orthogonal to the wave number k. So this is a classical construction of a basis of divergence-free fields. And these are called E in my slide. We multiply this E by theta, the coefficients theta k, which are radially symmetric, and in this way we construct the coefficient sigma. And what happens that with this construction that is in a sense the most natural one on the torus, we find what we wanted, namely that this elliptic operator is the Laplacian up to a constant related to the coefficients theta. So if we choose theta so that the L2 norm of this sequence theta is a constant k, we have what we want. And here in this slide, please see these two formulae which explain in Fourier what we do. if this is Fourier, we take these rings of wave numbers that go to infinity. This ring will go to infinity when n goes to infinity, and in this ring we take theta n, which decay the right way, and this is the spirit. So it is really small scale noise which affect the equation. I have to stop. Simply let me say that what we need, but I will stop here, we need to compare this elliptic operator with the projection, with this elliptic operator without projection, which is the Laplacian. And this can be done, is the most difficult technical part of our paper. In the next slide, I wrote an explanation, but I can send this slide to everybody to see the explanation if you're interested in. So let me jump to the explanation, which is a little bit technical, and simply say that the literature related to the paper, of course, is much larger than this. I want to mention this paper of Arnold, Crowell, Wichthuth that has nothing to do with the Navier-Stokes equation, but for me was all the life was very inspiring. These two papers that I already mentioned were very important. Galeatti discovered this principle, so it was the breakthrough to try to do that. And in these works, we developed the idea of Galeatti in several directions. Thank you very much.
So thank you very much. And are there questions from the audience?
So, sorry, I have a question. You consider the transport noise through the, and you remove what is called the stretching term.
Yes.
And but basically that's like your transport and the stretching term is actually a transport in 3D, like a Lie advection. What do you think on investigating further with this term? What are the results that you expect?
Okay, of course, as you can guess, it is the problem over which I spend all my time on this problem, clearly. Is extremely difficult, extremely difficult. I think that there could be progresses for passive magnetic fields, but for the 3D Navier-Stokes, only maybe after the progresses on the magnetic field, very slowly in time, if possible. So for the 3D, I'm not sure that one can ever succeed. For the passive magnetic field, yes, putting geometric assumptions between the objects. But it's really very, very difficult. If you just put both terms and you do the computation, you see that it doesn't.
Thank you.
Okay, so I think we thank Franco Flandoli again for the very nice talk. Thanks a lot.
Thank you very much.
Thank you. And the second speaker will be Peter Constantine from Princeton. He's going to talk about hydrodynamic pressure. So the floor is yours.
Thank you very much. First of all, thank you for the invitation. I'm really sorry that we cannot be in person, and this is really no real substitute for that. I'm very pleased and honored to speak to friends and experts and people that I know very well and people that I know a little less. So I'm going to talk about hydrodynamic pressure, and much of my talk will be on things that you all know very well, but maybe from the point of view of turbulence. So I would like now to remind us about some basic reasons, one of the basic reasons why we might be interested in singularities in Navier-Stokes and Euler equations, the behavior of small scales in turbulence. And turbulence is a very open field experimentally and theoretically in physics, and of course in mathematics. But there are a couple of pretty well-established results experimentally. One that is not written here, but it's, do you see my pointer? My hand, the little hand that I'm rolling here?
Yes, yes, that's visible.
So that's all my technology for today. So one of them is this epsilon, which is the rate of dissipation or negative rate of dissipation of the kinetic energy in some average sense. And this is experimentally and theoretically supposed to be bounded away from zero in the limit of infinite Reynolds numbers. And this parameter is one of the most important parameters in turbulence. So it is really the funny brackets, the braces are not well defined, but you can think of them as space, at least as space and time averages. And the two-thirds law, or fifth law, we'll see in a second, is essentially a statement of average Hölder continuity, provided the scale over which we're making a separation between velocity here and velocity there and take averages. The scale is bounded below by a small number, and the small number is the Kolmogorov cutoff scale. In physical space, it's proportional to the viscosity, kinematic viscosity to 3/4 and to inverse power epsilon to -1/4 of the dissipation rate. And the inverse of that is the cutoff in wave number. And so the Kolmogorov spectrum is experimentally very well established, and it has this form, a -5/3 power law with an exponent again that depends on the dissipation rate. And the 4/5 law, which is a version with power 3 here, it's called 4/5 for reasons that have nothing to do with the powers. It has to do with the prefactor here. It's roughly speaking, very roughly speaking, saying that the third power of the displacement is of the velocity increments across the displacement L is linear in L. So they all smell like 1/3 Hölder continuity. So turbulence is, as I said, a very, very open field, and the correct framework validating and predicting experimental evidence is not well established. So it's there may be a relation to Navier-Stokes, but because it's the only thing that is, let's say, for the large scales, very well established, but it's not clear how to describe it. And in particular, this universality that was written with the funny brackets there is not entirely clear how to get to it more rigorously or more theoretically. And one of the obstructions have to do with behavior of small scales, both in terms of the displacement, so displacements of order L, and in physical space. And the result of that are corrections to the 1/3 power. And they're written here with the large scales L entering as a factor. So you can think of them as corrections of the powers. In this case, the zeta p for Kolmogorov will be p times 1/3. Or you can see here, alpha p is the correction power. And this u here is really defined via so you can think of u as being defined by the large scale and by epsilon. There are theories, all kinds of theories in which they're running around here and deducing epsilon from some u, but they're not rigorous theories. So very little is known rigorously, and I don't want to belabor that. Essentially, it's just what you all know about Navier-Stokes, massaged and averaged, and you get some inequalities that are not saying much. So in the case of this talk, I will argue that the pressure is very important, both for Navier-Stokes and the Euler equations. So the pressure is not really, for sure, the kind of pressure that you have in compressible flows where you are expecting a compression and an equation of state. It is obtained just by insisting the divergence-free condition on the equations, and therefore it takes this equation, Laplace P is the divergence of u dot grad u, and because u has to be incompressible, you can compute the right-hand side in various ways, and you can see it, if you wish, that it's a second derivative of u squared. So the pressure is defined up to a free, possibly time-dependent harmonic function, as you see here. There is the same equation for Navier-Stokes and for Euler, and actually also for a variety of hypo or hyper viscous cases if you don't have boundaries. And in the whole space, if you ask the pressure to vanish at infinity, and which I will, then you can represent the pressure using the second order of the U's as a product of Riesz transforms applied to the tensor of U with U. So there are very famous sufficient conditions for regularity, which I'm going to remind here. And I'm going to give you a slightly different perspective on them. So here are the Prodi-Serine conditions that are very familiar to people who ever study Navier-Stokes, and in particular, the one that I'm writing down is the extreme case in which Q is infinity, or the other extreme case where Q is 3. They're very different. So this case leads to a condition on anomalous dissipation, and this one doesn't so trivially. Okay, so the first conditions were proved in various ways, but the case where Q equals 3 required a very different proof by Skariazis-Seragin and Schwerak, and it is a little less quantitative. Although there are recent results by Terry Tao and by others that improve the lack of quantitative nature, but not sufficiently to be useful for turbulence. So there are conditions in terms of pressure, and one significant condition is easy to state. It's in terms of the L3 norm, and it's also very easy to prove that this condition implies regularity. So it's a second power in time. And there are other conditions in terms of the pressure that are, again, of a nature that are not immediately clear how to use them for anomalous dissipation. So I want to state two more that, so one that is the time integral of the gradient of U in L3 squared implies regularity. This has the same scaling as the UL infinity, and in particular, it has the same usefulness. I'll show a slide at some point as the U in L infinity. And it is really very easy to prove. And then the second one is that if the pressure is continuous in L3 halves, then U is regular. So this one, you see here, this one also is relatively easy to prove, or easy to prove. I'm going to show you a little bit maybe of the idea of the proof, I don't know, depending on time, of this one in the context of another condition that I'm going to describe. But notice that this is like the L3, the Skariazis-Seragin condition, because the pressure is, roughly speaking, like U squared. So this would be a stronger in some way than the Skariazis-Seragin condition if you replace the continuity in time by L infinity. And I don't know if anybody actually, I really couldn't find this in the literature, but maybe others can find it. I wouldn't be surprised if somebody thought about it, they could prove it. So the question is if somebody tried to prove it or not. So there could be relatives of this that have been done in the literature. the one on top is very, very easy. I think, however, nevertheless, I think is very important. And, you know, it reminds me of a comment that Peter Lax made to me once when I showed him something and I said, oh, this has an embarrassingly easy proof. He replied, embarrassing, yes, but to whom? So it is an easy, very embarrassingly simple proof, but it is maybe a useful concept. So I will come back to this a little later. So there are lots of things known about Navier-Stokes, and they are in some sense related to intermittency. So there are higher derivatives that are bounded in various time integrals with exponents less than 1 if m is larger than 1. And these are exponents that are obtained by Fourier-Guillaume and Temam in the 80s. They have interesting consequences, but they constrain to some extent the nature of the singular scenarios. So one already observed by Tartar around the same time as the Fourier-Guillaume and Temam is the fact that the maximum length that you can throw things in time t ballistically by velocity is finite. And so this integral power 1. And remember the difference between power 1 and power 2 here, regularity is done with power 2. I wrote here, just by contrast with the previous thing that I said, that this is a regularity condition, and this is easy to prove that is follows from Fourier-Guillaume and Temam, and is known to be finite. Again, this is the same scaling as this other one. It doesn't follow, neither one implies the other directly, but the proofs are easy. The L infinity norm, so the maximal stretching rate, is integrable to power 1/2. And that's a limitation that is important to know. And there are other quantities. Using the vorticity, you can obtain Laplacian almost to power 4/3. It's essentially in Lorentz spaces. And although this started way back, there is a recent result that goes with this Q almost to 4/3. So it's a condition that, again, is of the kind, but not a consequence of the Fourier-Guillaume and Temam. I can remind people, if they didn't know how these are obtained, you take, in this ones, you take the velocity equation, and essentially, if you want to differentiate, but then you divide by the quantity, they're integrable in time. And here you take the vorticity equation and do something like that. So for the Euler equations, the story is different. So I'm going to come back to the importance of the pressure. So I remind here everybody some things that everybody knows about the Euler equation. So smooth solution, I'm not talking about models. So the Euler equation themselves, you can have blow up if the energy is infinite. So for instance, for solutions of this type, which are 2.5 dimensional, the dependence in Z is explicit in the infinite dimensions, and there is a stagnation point. So there is a not so recent, but a great result by Tarek that shows that C alpha of vorticity can blow up in a case of smooth axisymmetric solutions without swirl. So it's without swirl. The result of it, Tarek, is without swirl, non-smooth. It's C alpha with alpha small. In the case of smooth axisymmetric solutions, this result cannot hold. So the reasons for this have to do with small scale isotropic behavior of the Euler equations. And if you impose symmetry in general, the isotropic behavior destroys the structure that allowed a blow up. So there is suggestive numerics. And my 2 cents worth of comment here, this is just something that experience both in analysis and some numerics suggests is that underlying the blow up, there is a structure in physical space where the blow up occurs, and that structure cannot stay smooth as the blow up occurs. So, and that's just a suggestion, it's not a theorem and not something that I, how should I say it? There could be very unstable situations in which there is a squeezing of an object, but in incompressible cases, which is what we're talking about here, there needs to be also some escape routes. And then because of the escape routes, you have strong asymmetric behavior at the blow up, and asymmetric behavior means a collapse in some directions and non-collapse on the others. And at the end of the day, the underlying geometric object cannot be just simply a line or a point. So for the reasons that I'm going to show in a second, we know that there is a mechanism of geometric depletion. So if the vorticity direction is smooth in regions of high vorticity, Navier-Stokes solution is smooth, and the Euler equation require infinite velocity for blow up. In other words, the Euler equation transports the blow up point to infinity. So there are improvements of these results that are classical, and they go a long time ago. And there is a little story that I like to say. Again, it's not rigorous, but it's important to repeat. The fact is that coherent vortices do form. So these are strong vortex tubes. They become narrow and intense, and they approach each other at various angles. And when they are coming close to each other at various angles, they violate an assumption of a smooth direction field of vorticity. But there are some bounds due to viscosity that tell you that this cannot be too violent. Well, this is a very weak bound, but it tells you large, this object gradient, which is the distance between two vortex tubes of very different vorticities, this distance cannot go to zero compared to the viscosity. So then there is a reconnection. It's a change of topology, which is prohibited in smooth solution of Euler's, but permitted in 3D Navier-Stokes. And the reconnection events can happen several times, and they do happen. And they are common in plasma physics, and they're common in the solar corona, and they are followed by a great dissipation event. In other words, there is a great release of energy, and there are natural regularization mechanisms in which the rate of decrease of energy is enormous. So that's, not rigorously proved, but it's not rigorously not proved either. So I want to mention two conditions in terms of the pressure. So the first one is joint work with Dongo, Che, recent 21. And I remind on this very busy slide, I remind some notation about the Euler equations and transport. So we have the Lagrangian map is called capital X. The Lagrangian ODE, time derivative of velocity, material derivative is d sub t, and we decompose the gradient in physical space into the rate of strain and the vorticity, essentially, antisymmetric part of the rate of the gradient. And everybody knows the stretching equation, which is written in this form, material derivative of vorticity S omega. And many people have studied the rate of change of the rate of strain. And this is what I'm going to call in this talk the S equation. It's the equation for the symmetric part. And there are three terms here. There is the positive S square, the negative J square, and the Hessian of the pressure. J square is negative. It's symmetric. It's actually proportional to the projection orthogonal to the direction of vorticity. And so it is opposing a blow up. The pressure is perhaps opposing or perhaps not. So this is an equation that I'm going to refer to in a second as the S equation where a little later. Alignment is due, or the depletion, geometric depletion of nonlinearity that I mentioned before is due to the stretching term. The stretching term can be written as a scalar that's an integral of the magnitude vorticity, and the scalar vanishes locally, or it's less singular depending on how the direction is smooth or not direction of vorticity. So that's the source of the geometric depletion of nonlinearity. But now I'm going to talk about this Hessian of pressure. So first of all, there is an old blow-up result. So the statement in words is that if the matrix is non-negative in a weak vorticity region carried by the flow, then there is blow-up. And the reason is the S equation. So in this one, if the vorticity is weak in some way, you'll see, then J squared doesn't bother you. S squared is always really the square of S. So I'm ODE, if I would neglect it, it would be if J is neglected and P wouldn't bother me, I would get blow up. And that's what that statement is. If P is non-negative on a trajectory, then there is blow up. So the precise result I'm going to paraphrase here because it was written in some paper in 95 on Physical D, I think. So if you mark a point and assume that there is a time, which is a coherence time, I call it, with the two properties. First, that the vorticity is bounded this time interval along this particular trajectory. It's bounded, and the bound is called capital omega. And the second property is that the pressure is the Hessian pressure is a non-negative matrix. So in other words, for any vector, it's P, V applied to V is non-negative. Then if the initial data are large, so in initial S is large at A. So by large, I mean compared to this predicted bound. So it's large in some direction negative. Then blow up occurs if the coherence time is long enough. So that's exactly essentially quantifying the idea that I gave just before. If pressure is non-negative, I can throw it away, and or how large the contribution is doesn't bother the blow up of S. So I want to remind people that in experimental situations, in many cases, in order to follow the vortex stretching, people place particles at minimum of pressure in actual fluids and follow the behavior of minimum pressure. Now in incompressible fluids with the pressure defined by the as a Lagrange multiplier, the pressure is not non-material. So following at the minimum, of course, this would be non-negative, but it can cease to be a minimum in a short time, and then that can avoid a blow-up. So that's what this theorem says. So the result with Dongo is, I'm sorry for the technical look, but I'm going to make some comments, is that a certain quantity, if the exponential of a double time integral of a certain quantity, which is explained below, which in terms of the Hessian of the pressure, if that is finite, then there is no blow up. So the quantity in particular, in order to make it more clear, if you are assuming that you have some sort of a self-similar behavior, then as you know from Bill-Katomida, omega should blow like 1 over t, and one gradient of omega, or the two gradients of the pressure, should blow like 1 over t squared. And the statement here says that if the factor here is less than 1, so if t minus t squared times this Hessian of pressure object is less than 1, then there is no singularity. So this vector, you take the Hessian of the pressure and to the direction of vorticity and dot it into the direction of the evolution of vorticity. So it's a very physical or dynamically relevant quantity, and you are looking only at the negative part of that scalar. So because obviously these are two vectors, unit vectors, this is less than the matrix norm of the Hessian of the pressure. So in particular, you have this condition that says that the double time integral exponentiated needs to be finite. And in particular, as I said, if the size is blowing up with a prefactor less than 1, so this is what's called type 1 blow up, but the constant here is less than 1, then there is no blow up. So this result in some sense is surprising because there are models that model the pressure and then they get blow up and they ignore it in some way. So there is a famous model by V.A. Foss, which is a very simplified model in which all the pressure is replaced by a local term, or a model that I did a long time ago in which you replace material derivative with time derivative, which means you replace the pressure by some double Riesz transforms, the formula in physical space. So you just drop the U dot grad term. So in that case, there is blow up. And the previous example condition says that pressure alone is enough to stabilize. So the reason why this is a little surprising, again, is the S equation. So in the S equation, you see control the pressure itself is a little surprising that if you look only here and you know that the pressure is of a certain type, you wouldn't know that this stops the blow up. But of course, it's a nonlinear equation. So there are other reasons why it's important. So I'm going to go now to the condition that I wanted to mention regarding Navier-Stokes and pressure. So for that, I have to remind us of some representation of the pressure. And bear with me for a second. So we take spatial average on the unit sphere. So this is spherical averages, not the ball, but the unical sphere. And then you have a famous Poisson-Darboux kind of relationship, how the Laplacian is averaged. And we define an object that is akin to the pressure average, but you add a little longitudinal energy here. And the reason for that is that it results into a local equation, which I call the monotonicity result. If it had a sign, it would be a monotonicity result. It tells you that this quantity has a local equation. I'm not going to belabor this. This is an old result, but it's a very important, has important consequences, and I want to describe them. So the important consequence is, okay, so I'm sorry, these W's are differences. So this is a quadratic expression with differences to a reference V. V can be anything. And these are, of course, on the unit sphere, they're bounded objects. So the representation formulas that come out of this, at any scale R, you can break the pressure into two pieces, and both pieces require information at distance no more than 2r from x. Beta is, and you'll see it in a second, it's an explicit average of p at distance less than 2r. And as you recall, the pressure is defined up to harmonic pieces, but beta minus p minus beta vanishes for harmonic functions, so this removes the harmonic component. And beta obeys bounds which imply global irregularity. At each r, if you fix r, if pi would be neglected, you would get global irregularity. Pi has an explicit integral representation in terms of squares of increments. So recall that we are really interested in making contact with intermittency and with conditions about structure functions. And pi vanishes quadratically in R for almost all t. So this is saying that I have a right to neglect pi, of course, if I'm not very precise mathematically. But if we could really neglect it, we would have had regularity for Navier-Stokes. So these are main properties, and beta is really just a cousin of the spherical average. This is not the volume average. So it's an integral on the annulus with a singular but not very singular color. Okay. So more precisely, this is a horrible expression so that you see that it's explicit. So for pi, and I'm not going to belabor this. It's an formula because I chose a certain weight here, and you can make millions of other representations of this sort. So as I said, the bounds for beta are non-trivial because of this monotonicity lemma. So the first bound tells you that beta it's a bound useful for Euler equations, for instance, is controlled at each r by the kinetic energy. And remember that morally, the pressure is a double Riesz transform of U. So the Riesz transforms are not bounded in L infinity. So having an L infinity bound for the object is very useful. And again, this is somewhat related to the issues that I'm going to mention regarding anomalous dissipation. So for similar bound, you obtain in terms of the gradients, which is useful for Navier-Stokes equations, with a less expensive bound. So these follow from the monotonicity lemma, as I said, and hardness inequality. So of course, because of known bounds, we also know that the beta is like U square in LQs that are other than infinity and 1. So that tells you that you can go almost to A equals 2 and get bounds for that are less expensive for gradients. And in particular, you use, so in some sense, you can think as beta getting rid of one derivative. So if you are looking at this bound here, if beta would be at a pressure and I would trade this gradient for an R, I would say that the pressure is bounded in L2 by U in L4 squared, which is true. And here I have a gradient that I traded on R. So beta is in some sense more regular. So should any of these bounds hold at fixed P, at fixed R and hold for P, then we would have regularity. And it's a very simple, I give some arguments for that. I don't want to belabor that. Okay, so these are subcritical bounds, meaning that they even a little worse bounds will be enough for regularity. But of course, we don't have them for Navier-Stokes. So pi is of this type. This is a rough bound because of the velocity for small distances. So in particular, it tells you that pi in any LQ, not 1, goes like R squared compared to the gradient in L2Q squared. So you can prove pi less than a constant times R squared because of this in L3, but the constant is not time integrable. The constant is time integrable to the power 1/3. So almost everywhere, pi is less than R squared. So in some sense, you would like to neglect it, but we don't know how. So this is the Vercelli-Galdi result in some sense, and we're going to revisit them. So I want to slow down here for this slide because it explains why I care about these things. So the Reynolds number is formally defined in terms of the inverse viscosity, but you need a reference velocity. And the reference velocity might be an issue. So if you refer to the initial data in L2, you would have to also have a length scale. a very natural Reynolds number related also to the Skoriaza-Seryogin-Schwerak result is this quantity, the L3 norm divided by nu. So you can think of high Reynolds numbers in terms of this quantity. So similarly, a cutoff number, highest wave number, is the ratio between gradient U and L3 that I mentioned before as being an important quantity divided by UL3. So this cutoff number, to a large extent, if I would know really what behavior up to this cutoff number is, I am arguing that it is really not important what happens after that. I mean, for the turbulence, not for Navier-Stokes blow-up is a different issue, but it's important to know what is the dynamics below this cutoff number. So the sufficient conditions for regularity imply inequalities, and in particular, the ones that can imply inequalities, they imply inequalities that are valid on weak solutions already, and they are clear inequalities with constants that don't depend on anything, and they are related to putative lower bounds on the dissipation rate in freely decaying turbulence. And so if you are assuming that in freely decaying turbulence, you are bounded, epsilon is bounded below by 0, this quantity, this product needs to be bounded below by 0, by a quantity different than 0. So if there are two ways of having this bounded below. One is that the ensemble is such that this quantity by itself is bounded below. So in other words, initial data have very large gradients. This can be done for solutions of Navier-Stokes, and I actually have done it. I'm not going to, but I mentioned it in previous talks. There are constructions of steady solutions of Navier-Stokes with varying viscosity, time-independent solutions for which this quantity is bounded below, and there are solutions with forcing that is bounded in some LP spaces. So if this quantity is bounded below, then you are discussing a different problem. But if you are discussing problems in which the initial data are, let's say, bounded in L2, an ensemble in which the energy is controlled, but the entropy in the initial data or the entropy in itself is not bounded, then this quantity needs to go at least like log of 1 over nu. And that's essentially the interesting regime. It can go much worse if you have blow up in Navier-Stokes, but the interesting regime would be when this quantity goes like log of 1 over nu. And the same inequality is true with this quantity. It's very easy to prove. So both these are rigorous inequalities for all solutions of Navier-Stokes, as long as you can do calculus with them. And it's exactly the same inequality with the quantity that I mentioned before as a sufficient condition for regularity. So if this is finite, you can divide by nu on this expression. I wrote the nu just because this is what is interesting. So now let's go to the criterion in terms of the pressure, the pi, the term that we neglected. Remember, the term pi is small. If r goes to 0, it goes to 0. So quantitatively, we can take a scale of velocity, capital U, which is at our disposal, and the number r that can be a function of time, I'm sorry. And assume that the L3 halves norm, remember this is the one that corresponds to L3 for U, is small, 1/2, so it's really the correct scaling, is smaller than nu at this r. And assume that this r is integrable to a negative power, large power, unfortunately, then the solution is bounded. So this is the criterion. I'm going to discuss it a little bit. The proof is not hard. I think I have 3 minutes according to the rules. So maybe I'm going to go to the comments and then the proof. The proof, let me just say the idea. So the condition implies a bound for U in L3, which we know implies regularity. So, and the main part of the condition is a critical condition to use the dissipation. So maybe I'll skip the proof so that people can ask questions. This is just a simple idea, so I'm going to come back. So let's make a few remarks about this. So first of all, if P is continuous in time, so is pi. So a condition on continuity of P in time will imply a condition of pi continuity. For U large enough, then the measure of where I put the condition for pi is small by just Markov-Chebyshev. I grew up with this being called Chebyshev inequality. Okay, so simply the energy is bounded and the measure where it's large needs to be small. So if you assume pi is continuous in time, which is a weaker assumption, of course, but it's then you can guarantee that this pi, this condition that I imposed, is small for an R that's even time independent. Okay, not integrable, but really bounded, even bounded away from zero. So therefore, the regularity follows from the criterion. So in other words, what I'm saying here is that the condition that continuity of P in time with values in LR3 halves implies regularity is a consequence of continuity of pi in time with values in L32 implying regularity, which is a consequence of this previous criterion that I said that says that you need an R of T that's integrable to a negative power. Okay, so that's one comment. And the other comment is that there are easy to prove subcritical. This is a critical quantity. They're easy to prove other quantities that are interesting by themselves also. So for instance, the cubic power of pi 9/4. Again, every condition like this will imply the corresponding condition for the pressure. And in particular, the Berselli-Galdin, they're easy to prove that pi L3 squared implies regularity this way. So I think my time is up. I'm going to go back to showing where the main part is. So here in this proof, there is one term that is the one that uses the inequality. And that term is when you cut off for large U and you're obtaining this quantity, which is the L3 half norms, multiplying the dissipation that you get from the Navier-Stokes. So the quantity here needs to be less than the dissipation in Navier-Stokes. All the other guys are controlled, and in particular, the beta guy is the one that is controlled in a way that requires you integrability in time of R, the negative power, or of course, if R is time independent, it doesn't really matter. So the outside piece is the one that causes problems because you assume the inside piece, that this one is small. So I'll stop here.
Thank you, Peter. Are there questions or remarks from the audience? So you can unmute yourself. I see some people clapping. So if you want, maybe Gautam. Hi, Gautam.
Hi, Peter. Thank you. It's nice to see you virtually, right? I had a quick question. If you could go back to this log new business, right?
Yeah.
Yeah, no, I'm just, I guess it's more of a comment. I find this very interesting because this log new sort of scale comes up exactly when you have I guess the dissipation enhancement. The best scales, I mean, the best you can do with mixing velocity fields is this sort of log new enhancement, right? I don't know. I was wondering if you could comment more about this.
Okay, so I don't, I'm trying to find the actual thing. I think it was further down, and I'm gonna, so I'm gonna say comment. The comment is just a mathematical comment. Let me find it first so that I can be on the same page with, okay. So there is this stretching. So suppose you are dealing with smooth initial data, and therefore you are really asking yourself whether or not things become singular. So the quantities that we are describing, whose control implies regularity, these quantities, especially the ones based on L3, are so based on this smaller scale, are critical in the sense that if you give yourself the luxury of having small data, these quantities multiply the dissipation and become absorbable by the dissipation. Or in the language used in some sense by the stochastic, the Franco's talk, if you control these terms by enhancing the dissipation via a stochastic process, then you delay the blowup because you get a larger coefficient of the Laplacian, and these guys are really fighting just directly the Laplacian. You have no other control. So they are not dynamic in some sense. If you look at the evolution of L3, in some sense, L3 itself is useless because it comes as a coefficient in front of the dissipation. You cannot use it to absorb unless it's small. So that's why the result by Escariaza, Schwerak, and Seryogin is critical. It's really not allowing you to do a quantitative bound directly like of this type of the gradient. So what I think is happening is that you have a mechanism here in which you get the dissipation without blowup, okay? And that dissipation without blowup is strong enough to have a lower bound. And that, I think, is something mediated by diffusion and not so it's for a sequence of solutions and not for the Euler equations. So
that's interesting you say that, because this is exactly, I mean, even in the linear problems, when you look, you have this log mu scale that comes up there, which is one version of the bound, but I guess I'll ping you about this a little bit more later, I guess.
So I don't know how to do that in the nonlinear problem. So that would allow you to actually state a theorem. So, and also I didn't discuss this capital T. This capital T in the freely decaying problem, of course, is limited. But order 1 is already very interesting, or even small, but not as small as, you know, the trivial amount.
Okay.
Many thanks. Any more questions or comments? Okay, seems not to be the case. So we thank Peter again for the nice talk.
Thank you. Thank you.
To clap. So now we have a longer break of about 40 minutes, so until 4:30, so Central European time, and the next talk will be by Elio Marconi. Okay, so I would propose we start. So so the next talk will be by Elio Marconi from Lausanne, and the topic is going to be regularity of the flow of two-dimensional autonomous divergence-free vector fields. So please, Elio.
Thank you, Gianluca, for the invitation and for the introduction. I'm glad for having the possibility of speaking about this topic that we started in collaboration with Paolo Bonicato, who is also in this conference when we were in Basel in the group of Gianluca. And so I cannot scroll. Yes. Okay, the first slide is very introductory, just mainly to fix the notation. So we consider a vector field B, which, okay, at the moment could be also time dependent. And we consider two problems related to it. One is the ODE, so the equation for the flow function, which we call capital X. Okay, And the other one is the transport equation driven by the vector field B, and we call U the solution of this transport equation. Indeed, we will mostly focus on the Lagrangian parts, so the ODE, the equation, the regularity of the flow. And of course, in the Lipschitz setting, which is the classical setting, you can solve the PDE using the method of characteristics, so in terms of the flow, and you have that U is constant along the trajectories detected by the flow, and therefore, if you want to know the solution at time t in position x, you go back along the characteristics and you evaluate the initial datum at the initial point. And okay, so this duality is maintained also in the non-smooth setting, has been extended to Sobolev and then to BV vector fields with this constraint that the divergence is in L infinity by the Pernell-Lyons and Ambrosio respectively. And okay, we have this duality once we introduce the correct notion of flow, which comes out indeed from this duality itself. And this the notion is the notion of regular Lagrangian flow. So the first condition is just the integral form of the standard differential constraint for the flow that it detects integral curves of the vector field B. And the second condition is a constraint that in the smooth case is a consequence of the divergence being in L infinity. Okay, that it says that the flow cannot compress too much the Lebesgue measure. And okay, so the well-posedness in this for this regular Lagrangian flow is originally obtained from the well-posedness of the solution of the transport equation of the PDEs, but we will see there is other approach directly which are Lagrangian. And let me mention just two remarks which are not strictly relevant in the talk of today, but they are important recent developments. So the first one is that the second condition is actually not a consequence of the first and the constraint on the divergence. Indeed, in this setting, you need to put as an assumption, and it works as a selection principle for the flow, and select a unique flow. And also that the divergence of being in L infinity for a flow can be removed. Okay, in the BV setting, this is a recent result by Bianchini and Bonicato, and of course we need to slightly reformulate if you want the notion of regular Lagrangian flow, in particular the second condition. And okay, we'll not enter more into details on these remarks. And what can we say about the regularity? So the first thing you do in the classical setting, if you want, is that you can differentiate the equation for the flow. You have an evolution equation for its differential, and you can estimate by an easy Gromwald type argument. You can estimate the norm of the differential with the exponential of the integral of the differential of the vector field P integrated along the characteristic line, along the trajectory of the flow itself from 0 to T. Okay, you see immediately that if you start from a Lipschitz vector field in space only, what you get is that also the flow is Lipschitz, and the constant will be bounded by e to the LT. And but in general, due to this expression, you don't expect that if you have an integral bound like an LP estimating the differential of the vector fields, you deduce an integral bound on the differential of the flow. Okay, this is because you have this exponential expression, and you don't expect this additional that you can actually improve very much this estimate. There are precise example. Actually, the situation fails more drastically. There are you can't even obtain. You can disprove the propagation of even fractional order regularity for the differential of the flow, and you can almost saturate, let's say, this quantity. And the examples are from Chabin, and more recently also from Alberti, Crippa, and Mazzucato. And you have some positive results also, which tends to say that the gain that you have, the improvement that you have on the integrability of the, if you want, of the derivative of the flow, the regularity of the flow is just a logarithmic correction. So you don't have any fractional order. So the flow will not belong to any fractional Sobolev space with, let's say, positive differentiability order, but you have just a logarithmic correction. And these are These are recent. Okay, there is this is some way implicitly already present in the paper by Cripp and Ellis, which is the Lagrangian alternative to the theory I wrote before, which is directly working on regular Lagrangian flow, and it is more explicitly proven recently by Brouwer and Guyen. Okay, let me mention more in details the result by Cripp and Ellis. This is a Lewis-Lipschitz type result. Okay, so it means that we can remove a small set, for example, in the ball of radius r, we can remove a small set, and the Lipschitz constant of the flow at a positive time t in the complement will be bounded by this expression that you see, you recover the exponential of the integral from 0 to t of the norm of the differential of the vector fields. And you have an explicit dependence also on epsilon. So this regularity, this is quantified quite precisely, both in terms of the differential of the vector field and also in the dependence on epsilon, which is the amount of the set that you want to remove. Okay, so this, okay, if you want a drawback, one drawback of this approach is that you need to assume that p is greater than 1. Okay, it is not known if you can prove this statement for p equal to 1. And okay, so this is one of the main results I'm going to present today, which is a result in the same spirit, but okay, under different assumption, and the result is also quite at the end. The estimate that we get is some way different. So the vector field. Now, okay, we can cover the case p equal to 1, or if you want even the BV, the case of vector field with bounded variation. And we assume that it is divergence free. Okay, but mostly, so the most restricted assumption is that it is autonomous and in dimension 2. Okay, so then we also get a Lewis-Lipschitz type result. So we remove a small set and we get an estimate on the Lipschitz constant of the flow on the complement. And this Lipschitz constant grows at most linearly in time. So this is okay, not as in the general case where the dependency is exponential, right? You see that if you take, for example, in the estimate above, that this quantity does not depend on time. Here you get exponential of t times the W1P norm of the vector field. And so we get polynomials, actually linear dependence on time, but we don't have any explicit dependence, neither in epsilon or in B. So in B, in particular, it doesn't depend only on all the L1 norm of the derivative, or if you want, of the BV norm of the vector field. Okay, the dependency is more subtle. And actually, we discover later that it cannot be proven an estimate where this constant depends only on the BV norm of the vector field B. Okay, so this is really something which is related to the long time behavior. So we cannot really get a uniform estimate at a precise time. What we get is that at t goes to infinity, the growth is at most linear. Okay, so let me mention that both these results, so the one of Cripp-Ellis and our more recent one, are okay. It is stated for regular Lagrangian flow, but indeed they have their own interest also in the classical set. Okay, it is maybe a little okay. In our case, could be a little simpler the proof, but okay, the core is still there. And yes, so let me say something about the main ingredients of the proof. So the crucial point is that we can, in the 2D autonomous case and divergence-free case, we can take advantage of this structure, Hamiltonian structure. So the divergence in R2 is like the Carl rotated, no? Then we can find a potential, an Hamiltonian H, such that B is the rotated gradient of H. Okay, the term Hamiltonian is appropriate since we have that it is preserved by the flow. Along the flow is constant. Okay, at least in the smooth case, in the classical setting. And when you're able to prove, so when this equality, so when it is true that H is constant along the characteristic, so you deduce, so you obtain as a corollary that the structure of characteristics is the same, okay, can be deduced from the structure of the level set of the Hamiltonian H. Therefore, the uniqueness problem, which is the most relevant in this setting, reduces to the uniqueness on each level set, which typically, at least for regular values, they are one-dimensional objects. So you reduce the 2D problem to a 1D problem. This program was carried on in very details by Alberti, Bianchini, and Crippa. They found necessary and sufficient condition on the Hamiltonian H in order to have the well-posedness of the PDE associated to the transport equation. And okay, so we are not interested in such a fine result on the assumption on B. We want to prove estimates, assuming that the gradient of H, so the vector field B, has bounded variation. Okay, so we have this result on the structure of the level set that says that for almost every value in the image, so if you want the regular values, the preimage is made only of finitely many curves, Lipschitz curves, and with finite length. And they have the property that along each of these curves, the total variation of B is bounded. And moreover, we have, this is important for estimates, we have this constant that the infimum of the modulus of B along this trajectory is bounded from below, far from zero. Okay, this CS is named after Sard, right? Because okay, if you want, this is a counterpart of the Sard theorem that holds for C2 function, where you are in 2 dimensions. Okay, here we are not C2, but we have the second derivative is indeed a measure. Okay, plus the yes. So this is the result, and notice in particular that by the last 2 properties, we can deduce that the curve that parameterize the connected component of the level set have finite integral curvature, and they can be parameterized by a Lipschitz function. Of course, all these constants really depend on the structure of the vector field itself and not only on its total variation. And okay, this is mainly the point. This is the reason why we cannot get an estimate which is uniform, but okay, only a constant which depends implicitly on the vector field B. And okay, now there is this technical slide that if you want to consider the regular Lagrangian flow, this is the structure is compatible with the notion of regular Lagrangian flow. So also in this setting, it is true. So that we can, that the trajectories of the flow are contained in the level set of H. Okay, and once we reduce to this one-dimensional problem, also in view of the lower bound of the modulus of B, then they are trivially uniquely determined. So the flow X is trivially uniquely determined for the regular values, while it is constant on the preimage of the singular values. And okay, so let me try to explain now quite briefly why we expect to get a linear growth in time of the Lipschitz constant of the flow. So the toy model is the shear flow. Okay, the shear flow, for simplicity, we take it on the torus, and we consider, so the vector field as this form. So only the first component is non-trivial and depends on the second variable, right? So we can write explicitly if Z1 denotes the point X1, Y1, okay? We can write explicitly the solution trivially of the flow. And of course, the vertical components is invariant under the evolution. So it's preserved in time. What is interesting is only the difference of the horizontal components that you can estimate in this way in terms of the distance of the initial point. And now, of course, the regularity on the flow depends on the regularity on this F, which is indeed the regularity of the vector field B. And assume, for example, that F is bounded variation. And therefore, you can find a constant, you can get this Lufin-Lipschitz type result. And in this case, you can have a very specific explicit dependence. So the dependence is linear in the total variation of B, and it depends like 1 over epsilon as a dependence in epsilon. Okay, so here we have a very specific explicit dependence. Okay, essentially what we would like to do is to reduce the general case to this one, to say that, yes, to reduce the general case to this one. And this is what cannot be done in a uniform way. Okay, so let me try to sketch a bit the idea of the proof. So in order to take advantage of the structure of this problem, I wrote we will look for cancellation. This means that the argument does not go as usually it does. Like we don't estimate the velocity at which two trajectories are spreading away one from each other. But okay, but we can take advantage of the structure in this way. So there is a trivial case, let's say, an easy case, which is when the two trajectories belongs to the same curve, to the same connected components of the same level set. Okay, in this case, the trajectory is prescribed. They are allowed only to move around this curve. It becomes a one-dimensional problem. And if you want, here we can prove that you don't have any blow up on the Lipschitz constant on the flow. And if you want, a simple reason could be that the quantity here, so the integral between the 2 points of 1 over the modulus of B, represents the time that you need, that a trajectory needs from passing from the point x1 to the point x2. And this, of course, is invariant in time since the problem is autonomous. Okay, so in particular, if you assume that, so we know that for almost every level set, we have that the modulus of P is bounded from below and from above. Then we have that the curve has a by Lipschitz parametrization, and therefore this quantity, so the quantity at time t, the distance at time t can control uniformly by a constant times the quantity at time, the distance at time 0. So you don't have any blow up in the Lipschitz constant at all. Of course, this is very specific. The most interesting case is when the 2 points does not belong to the same curve. Okay, now since we are looking for the long time behavior, you can imagine that in a first approximation, what is more relevant, okay, what is the first order, if you want, is the difference between the periods of the two trajectories. So what is relevant is the difference between the periods of the two trajectories, and the periods as the expression we wrote before. Now we integrate on the whole curve, 1 over the modulus of B. And so we have a lower bound of B. So this function, 1 over x is 1 over CS square Lipschitz, if you want. And now suppose that we are able to map in a proper way, not to basically behave the way one curve into the other one, like you do trivially in the shear flow. Then you expect to be able to prove an estimate of this kind, that the difference of the periods can be controlled with the total variation of the vector fields in the region inside the two curves times 1 over CS square. Okay, here I'm hiding most of the technical part of the details of the proof that, okay, so the geometry of these curves enter into play. So here is what you cannot do. Here is really what you cannot do it uniformly. Okay, this really depends on the structure of this constant that is neglected here, depending on the structure of this level set. Okay, essentially this is the key point. Once you're able to control the difference of the period, you can control the long time behavior of this of the Lipschitz constant of the flow. Okay, so this is what I wanted to tell you about this result. There is an application to mixing. We can consider both the geometric and the functional one as a corollary. Once you have a regularity, for a regularity estimate for the flow, you can provide lower bound for the mixing scales. Okay, now I introduce the geometric notion. So since here we work on the plane and not on the torus, we assume, for example, that the ball of radius 1 is in invariant region for the flow. This is, okay, the fact that the ball is a particular choice, of course, but the assumption itself is not really restrictive, because when you have an autonomous vector field, each level set, so each closed curve containing a level set, okay, each level set contains, so the regions inside this curve is an invariant region. So here we are just assuming that, it is B1. Okay, so the scale, we say, okay, the scale of mixing is the smallest delta, for which at time t, we can consider any ball of radius delta, and the image through the flow of our initial datum, our initial set A, covers at least a fraction k. This parameter is called accuracy. Covers at least a fraction k of this ball. Okay, so you see at least a fraction of gray points and at least a fraction of white point in every ball. Okay, as anticipated, you call the smallest scale, the smallest delta for which this is true, you call it geometric mixing scale. And okay, another strictly related notion is the one of functional mixing scale. That in this particular case, when you take this specific initial datum, which is the characteristic of the set E, okay, if you want to have average 0, you subtract the characteristic of the complement inside the ball. You consider the solution at time t, which is just the characteristic of the image of the set A minus the characteristic of the complement, and you call functional mixing scale the homogeneous H-1 norm of the solution. Okay, they are not equivalent, completely equivalent, but they are strictly related, and indeed the conclusion for both this notion is the same. So as a corollary of the linear growth of the Lipschitz constant of the flow, we have a 1 over t lower decay, so a 1 over t lower bound for the decay of these mixing scales. Okay, the constant here, as it is for the positive result. Okay, in the case of the geometric mixing scale, depends also on the accuracy parameter, so the fraction that you want to see. It depends on the vector field, and not only through its total variation, and it depends on the initial datum. Okay, and the lower bound is also the form C over 1 plus T. Okay, if what you can do a bit more precisely is that if you assume some regularity on the initial datum, you can get a more explicit dependence on this constant. In particular, for when the initial datum is the characteristic function, if you take it with finite perimeter, the constant will be of the dependence on the perimeter will be like 1 over the perimeter of this set with initial datum. Okay, so since we have few minutes, I just mention some recent development. So, okay, as I told you, in general, you cannot expect that the flow inherits the BV or Sobolev regularity of the vector fields, but there is some very specific situation where this happens. Okay, and the setting is okay, the one before, and with some assumption more. And so assume, for example, that the vector field is continuous. Okay, this could be relaxed, but for the moment, let's assume it, and divergence free. And we consider the set of points. So the problem, as you may noticed also from the previous slides, are the points where the modulus of B is equal to 0, indeed, right? Where the points where the vector field vanishes. So here we consider the preimage of regular values. So this omega will be the preimage of regular values, so where we know that the vector field doesn't vanish. Okay, so if we reduce to this set, we have that the vector of the flow inherits the BV regularity, at least locally, because you have that this regularity depends on the lower bound on B on this set. So at least locally it inherits the BV regularity, and moreover, if you assume that the vector field is Sobolev, then also the flow will be Sobolev. Okay, so essentially we would like to apply the sketchy argument that I presented for the shear flow, or at least make precise estimate of this kind. And what you need to do so is that locally you need a direction for which you have this lower bound. Okay, at least locally. That's why I assume, for example, continuity. And okay, so this is actually you need this property, otherwise the theorem is not true. For example, if you just assume that you are positive in one direction but not far from zero, you can produce an example of a vector field which has any Sobolev regularity up to infinity, but the flow is not bounded variation. And also here, if you want, you can exclude also fractional regularity and so on. And okay, let me mention just that a motivation of this last result, even if it is very demanding assumption, was this recent result by Colombo and Tione that were able to prove a counterpart for regular Lagrangian flow of the standard Frobenius theorem that says that when the Lie bracket of two vector field vanishes, then the two corresponding flow commutes. In order to say so, they need the differentiability of the flow, at least in the direction of the other vector field. And under the assumption where you are able to prove that the flow is Sobolev, then you can deduce this result, this Frobenius part. This was kind of a motivation for this last theorem. So okay, this was all what I wanted to tell you. Thank you very much.
Thanks a lot, Elio. Are there questions or comments? So I have a small question to start about this. So this remark that you made about the quantification in terms of the BV norm. So do you mean that you don't have an explicit quantification, or you don't have uniform bounds when the BV norm is uniformly bounded?
Yes, you don't have uniform bounds. Yes, the examples is okay. You can just make it by tuning the parameters in your example with Alberti Bianchini Ripa, right? So the goal is to make this constant CS, the lower bound for the vector field, is small.
Okay.
And okay, and you can do it. I'm not completely sure that you can find an example, so a sequence of examples that saturate the exponential growth. This I'm not sure, but for sure you beat every polynomial. If you are not exponential, you are just tuning the parameter in your example, you become both exponential of square root of t or something like this.
Okay, you generate the rate.
I'm not sure it's sharp, but maybe you can also get the full exponential.
Because I was wondering, like a compactness argument, like so if I had no quantified estimate in terms of the BV regularity, then I would have a sequence of vector fields which are autonomous, equibounded BV norms, and the constant, in a sense, would blow up. So the constants in the regularity of the regular Lagrangian flow would blow up, but then I would have compactness of the velocity fields, and then but maybe that's the passage which would not work. Then I would have an estimate.
I think the problem is that the time is going to infinity. They are not all at the same. So the examples that you need make the estimate wrong at different times.
Yeah, you have several parameters. You have the epsilon parameter. That's true. Thanks a lot. Any other questions?
I have a quick question. I was wondering if you add a small diffusion, can you say something about the lower bound on enhanced dissipation rate? Do you think this is possible? Or
okay, well, I don't know, and okay, of course, all this structure, okay, is still there, but so. Oh, okay. Yes, the answer is that I don't know if you well, so you mean if you get some enhanced dissipation on things like this?
If you can say, oh, for an autonomous vector field in 2D, you cannot enhance dissipate faster than something.
Okay. Yes. This I don't know. I think that I did it in principle. Once you do this reduction to the essentially once you fix the geometry of the vector field, you have these constants, and you are almost in the position as like in the shear flow. But okay, so maybe you can get some result, but the point is that you don't have to rely on uniform estimates. So it's really for this specific vector field that you have. Okay, you have this structure, you have this estimate, and you can think, okay, it's not exactly like this that the works is done, the proof is done, but you can maybe think that this is a change of variable to the to a shear flow or this counterpart on S1. The trajectory are parameterized by S1, and you can think that it is like a change of variable, and you reduce to the shear flow through this change of variable map. Indeed, we were not able to prove it like this because the way of mapping one curve to each other depends on the two curves. You cannot do it in a consistent way with all the level sets. So you cannot do a single change of variable that works, and you reduce to the shear flow case. But I think that intuitively is almost the same.
But intuitively, the Laplacian will look very bad in these coordinates also.
Yes, it will look very bad. Okay, I think probably when you fix a single vector field, it will not look so bad, but the constant will depend on the vector field that you. So it depends on this change of variable that you have to fix a priori. Yes.
Thank you very much.
Is anything known for regular autonomous 2D vector fields? So is the BV regularity the issue, or is just you know, one could do something for regular vector fields in 2D in terms of enhanced dissipation? So
I can do it for shear flows.
shear flows, okay, but not like general regular 2D divergence-free autonomous. Okay.
No. So,
This geometric part is not much more difficult for BV than for smooth.
Regular.
So the constant that appears here, I'm not able to make it better in a smooth framework compared to BV.
Okay, so thanks again. Any more questions? Okay, so if not, we thank Elio again. Thanks a lot. Okay, very good. Let's start. And the last speaker this, well, afternoon or morning, depending on your time zone, is Gautam Iyer from Carnegie Mellon University. He's going to talk about anomalous dissipation in passive scalar transport. So please, Gautam. And you're starting 5 minutes later, so keep this in consideration for the time.
Okay. Thanks a lot for inviting me. Sorry for the technical trouble, right? I'm at Zoom's mercy. Let me talk about this joint work with Theo Drevas, Tarek El-Gindi, Inji Jeong, right, and myself, which we had maybe last year, right? So the main setup over here is I want to talk about passive scalar transport. Whoops, sorry about this. I'm getting used to this. Let me. All right. So I'm going to look at a diffusive passive scalar. So theta is temperature of a fluid, right? It evolves according to advection diffusion, right? I have U to be the velocity of the ambient fluid. So I have the U dot grad theta. I'm always going to assume U is divergence free and could be time dependent. Okay. So kappa is your diffusivity. I put that in front of Laplacian. And let's do it on the torus. So I'm going to do this on d-dimensional, right now actually 2-dimensional torus with periodic boundary conditions. Okay. All right. So first thing I'd like to talk about is, let's look at the energy loss, right? So since U is divergence free, right, we can just multiply by theta, integrate out, right? So the energy loss after time t is, well, if I look at half initial L2 norm square minus half the L2 norm square at time capital T, is just kappa times the integral 0 to capital T of the H1 norm square. All right. So what happens, right? So advection typically causes filamentation, right? We see this in fluids, right? And diffusion evens them out, right? So what's expected is that in certain turbulent regimes, there should be a balance, right? At which the rate these filaments are being created and the rate at which diffusion evens them out. And what you should get is that kappa times the integral of the H1 norm square, right, from 0 to T, should be bounded below by something that's independent of kappa. Okay, so I called it chi times the initial H1 norm. Here, chi greater than 0 is some constant independent of kappa. We call this anomalous dissipation. Right? So the result I want to talk about here is one explicit deterministic example of anomalous dissipation, right? It's not in nonlinear equations with Navier-Stokes. I can't do that yet. It's just one simple explicit example, right? And a couple of criteria that guarantee it. Okay. So let me start by stating the main theorem, right? And then we'll go into how this works out. Okay. So the main result is, okay, I'm going to choose psi to be the following set. Okay, so I'm going to look at pure harmonics, which is sine mx, sine ny. That's one of them. Or the other way around, sine of mx times cos of ny, or cos mx and sine of ny, and cos mx, cos my. Right? So these are just pure harmonics. Let's throw away from this 0 and throw away from this the constant 1, right? Okay, so result 1, right, which is, give me any alpha between 0 and 1. I can find you an epsilon, which depends on alpha. I can find you a chi, which also depends on alpha, both strictly positive. Okay, and an explicit velocity field u, right? In a certain regularity class, which I'll say more about that in a second, right? Such that, right, if my initial data theta naught is h2, and in a small cone around my nice set of harmonics, right? So remember this set psi of harmonics I defined up there, right? Take it, scale it by linear lambdas, you get a line, right? And I want my initial data to be in some small cone around this line, right? In that case, I can find you an explicit velocity field u that exhibits anomalous dissipation. Okay. Now let me go back and look at what I want about the velocity field u, right? So I claim it's going to be smooth up to time capital T, right? Of course, not at time capital T, something breaks over there, right? It's going to be integrable in time with values in C alpha. That was the alpha I chose, right? Alpha is strictly less than 1. Of course, at 1, it's not possible, okay? And it's going to be bounded, yeah? So that was the first example, right? And then I say, okay, if the initial data is not in this cone, what can you do? I can still exhibit anomalous dissipation. The only thing is now this constant chi depends on the initial data, right? Okay, so how does this work, right? So before I go into how it works, let me say a little bit about a quick corollary about non-uniqueness of the transport equation. Okay. So first, if I just look at the transport equation, dt theta plus u dot grad theta, right? If u is integrable in time with values in Lipschitz, right? Then certainly solutions are unique. We all know this from standard ODEs, right? Then the Dupont-Alliance theory takes this further. Instead of u being L1 with values in W1 infinity, reduce it and say u is just L1 with values in W1, 1. Okay, then you have this notion of renormalized solutions. These renormalized solutions are unique. There was this extension of Ambrosio. It said instead of L1 with values in W1, 1, you can do L1 with values in BV and still have uniqueness. And if you go lower, there are counterexamples, right? It's not unique. There's this example of Aziman, then Colombini, Lowe, Jeffrey Rausch, DePau, right? There's also this example of Gianluca Crippa, Giovanni Alberti, and Bianchini, right? So their non-uniqueness, maybe you can correct me if I'm wrong, right, is an example of U, which is C alpha, time independent, right? And it's an abstract existence proof, right? Some bare category type argument, right? So what we have, as a quick corollary to this anomalous dissipation result, is the following, right? Which is, give me any alpha between 0 and 1, right? There's non-uniqueness for an explicit velocity field U, which is in the same class I talked about, right? So it's bounded, it's integrable in time with values in C alpha, and it's smooth except at the time capital T. Okay. So you notice what I did here, right? Earlier my example was 0 to capital T. Now my example is I doubled the time interval, right? So why is this? Well, the proof is super cute. Let me show you the non-uniqueness first before going into anomalous dissipation, right? So here's one way to get the non-uniqueness, right? Let me choose U, the velocity field, to be the one from my theorem that gave me anomalous dissipation. Okay, so this works on the time interval 0 to time capital T. Right, it's integrable with values in C alpha. Okay, and then choose initial data so that this pair gives me anomalous dissipation on the interval 0 to capital T. Okay, now I'm going to cook up two solutions. First, from time capital T to time 2t, let me time reverse this velocity field. Okay, so ut is just u of time 2 capital T minus t. Then here are two solutions. First one, just take the Inviscid guy and time reverse it. Right, so theta solves the Inviscid equation up to time t, and between time capital T and 2t, it's just time reversed. Right. So of course, I mean, you have to check it's renormalized, but this is really no problem, right? So I have theta to be a solution to the transport equation on the entire interval 0 to 2t. What's the second solution? Well, let's take a viscous regularization. Okay, so I'm going to let theta kappa solve the diffusive equation dt theta kappa plus u dot grad theta kappa minus kappa times Laplacian theta equal to 0 with initial data theta naught. Okay, so you can do the standard Aubin-Lyons, send kappa to 0, get convergence subsequence, right? Let's call the limit theta bar, right? And of course, it's immediate to see that dt theta bar plus u dot grad theta bar should be 0, right? Now, how can I tell you that theta bar is different from theta? Well, here's a simple observation, right? If I look at the diffusive guy, right, the L2 norm of theta kappa, right, well, that decreases in time, so it's less than or equal to L2 norm of theta kappa at time capital T, right? Now at time capital T, well, the way I'd constructed my velocity field was to guarantee me some anomalous dissipation. So I've lost energy necessarily as kappa goes to 0. How much energy have I lost? Well, I wrote it down by this factor of chi over here, right? So at time capital T, right, necessarily my L2 norm of theta kappa is below L2 norm of theta naught by this factor, 1 minus 2 chi alpha. Okay. And so if I look at the L2 norm of theta bar, right, at time t, for any time little t bigger than capital T, you have to decrease, right? So whatever happened to this diffusive equation, right, I've necessarily lost energy, right, at time capital T, and from time capital T to time 2t, my energy is smaller. So whatever theta bar is, it's necessarily different from theta. So that's your non-union of this. Right. So, okay, so this is a super cute thing. How do you get the anomalous dissipation, right? Well, we do it in 2 steps, right? So step 1, we're going to prove a criteria on the Inviscid equation that guarantees anomalous dissipation. Yeah. And then on step 2, right, I'm going to find an example that satisfies these growth bounds. Okay. All right, so here's the criteria on the Inviscid equation that guarantees anomalous dissipation. Okay, so just to remind notation, theta is the solution to the Inviscid equation, and then theta kappa is the solution to the diffusive, the advection diffusion equation. I'm going to choose both of them to have the same initial data, theta naught. Okay, so my assumption first is that if I look at the Inviscid guy, theta, right, the H1 norm when integrated from 0 to t should be infinite. Okay, and then I want to assume one of 2 conditions, right? So condition 1 is if I look at L2 norm of theta at time t, no diffusion. So this is all theta, no diffusion. Yeah. So L2 norm at time t times the H2 norm at time t is bounded above by the H1 norm square, right? So that's the first condition, or alternately, I could replace it with the second condition, which is if I look at the H minus 1 norm at time t times the H plus 1 norm at time t, it's bounded above by some constant times the L2 norm square. Yeah. So assuming this first growth condition and then either one of the second 2 conditions, I guarantee you anomalous dissipation with an explicit constant. Right, so this over here is the diffusive guy, and that's the explicit, this constant C is exactly the same constant that shows up in either of my 2 conditions. Okay, so just a quick note, right? So the Inviscid guy, right? The L2 norm is conserved up to time capital T, right? So L2 norm of theta t is equal to L2 norm of theta naught, right? And now these 2 assumptions I had, they really reverse interpolation, right? So if I look for, if I just interpolate and I compute the H1 norm of theta at time t Inviscid, is bounded above by some constant times L2 times H2. Yeah. So this thing here, which I've highlighted, is really the reverse inequality as what my assumption was. Right? So I already know that H1 square is bounded above by L2 times H2, right? I need this bound to saturate, right? Which is I need L2 times H2 to be bounded above by H1 square, and then I can get you anomalous dissipation, right? Same thing with the H minus 1, right? I know that the L2 is bounded above by H minus 1 times H1, right? This is just interpolation. If this saturates, right, which is my second assumption, then I can guarantee you anomalous dissipation. Okay. Okay, so how does the proof work, right? So so initially when we submitted it, we had the slightly longer and convoluted proof. And then all of a sudden, right, Tarek wrote to us saying, hey, look, here's a simple lemma, which I can just prove with Cauchy-Schwarz, which simplifies everything, right? So here's the lemma, right? So let me take a sequence of functions in H1, okay? I'm going to assume, right, that let's say the H-1 norm of Fn times H1 norm of Fn is bounded above by L2 square, right? Just like my assumption before. Okay. I'm going to choose capital N as follows, right? So let me choose it to be this 1 over square root of 2c times the ratio of the H1 and L2 norms. Okay, so I probably should have said this before. I'm just going to assume everything is mean 0. H1 is same as H1 dot, but okay, I should have clarified. Okay. So if I choose capital N according to this, right? Sorry about this highlighting, right? So if I choose capital N, it doesn't work out, right? Then my claim is that the amount of L2 energy you have in frequencies larger than capital N is non-trivial, right? It's at least 1 over 2c times your L2 energy. Yeah. So over here, P greater than N is just the Fourier projection on large modes, right? Sorry. Okay, there we go. Oof. Okay. Sorry, every time I point to something, it highlights something else, but okay. Right. There's also another observation. Suppose my ratio of norms, H1 to L2, was diverging, right? This happens in our case. In the case that our ratio of norms is diverging, then I can guarantee you that my sequence Fn has no strongly convergent subsequence in L2, right? Because, hey, look, if this ratio norm is diverging, then this capital N that I've chosen here is going to infinity. So this tells you in the limit, I retain a non-trivial fraction of my energy at infinite frequency, right? So I can't possibly have a strong L2 convergence subsequence. Exactly the same thing is true if you look at the H2 balance, or H1, H2 balance. Instead of over here, I wrote down H minus 1, H1, right? So if I go back, my other assumption was L2 times H2 is H1 square, right? I can do the same thing for the lemma, right? And proof of the lemma is very elementary. You just Cauchy-Schwarz it and choose it the right way. It just works out, right? That's super cute, right? So if you grant me the lemma, what goes into the proposition, right? So I'm going to give you another lemma. I say, okay, suppose the integral of the inviscid guy, H1 square, diverges, right? So as I've said over here, the first integral, okay? And suppose I can find you some capital N that's time dependent, right? So, and N has to be like the H1 norm of theta up to a constant, okay? So suppose I have a non-trivial fraction of my L2 energy in frequencies higher than N, right? And just remember, N here is again the H1 norm up to a constant, right? Then necessarily, I must have anomalous dissipation with an explicit constant. Okay. So again, remember, my assumption is only on the inviscid guy, right? I want the inviscid guy to blow up and retain frequencies or retain energy in high enough frequencies, right? Which is comparable to the H1. Okay. All right, so if I take, just to point out, right, in the theorem that I stated for anomalous dissipation, I had balance assumptions guaranteeing me anomalous dissipation, right? If I look at the balance assumptions and I add to it lemma 1, it guarantees me this fact that I retain energy in high frequencies, right? So all I need for my proof of anomalous dissipation is that I retain enough energy in high frequencies. Once I have that, I can do the rest. Okay. So here's how the proof goes. Okay. So first, this is a linear equation at the end of the day. I can compare the difference between the inviscid solution and the viscous solution using the standard multiply and integrate by parts tricks. All right. So, okay, so theta, norm of theta minus theta kappa in L2, the way I wrote it is as follows, right? So I want to take 2 kappa times integral 0 to t of h1 norm of theta kappa square root, and then 2 kappa times integral 0 to t of L2 norm of the inviscid guy, theta square, and then square root, right? So here are 2 terms on the right-hand side. Now, if you look, right, the first term in red, which I've shown, is what I want to stay large. This is my anomalous dissipation one, right? Suppose it doesn't. Okay. So suppose my kappa times the integral 0 to t of h1 norm of theta kappa square is less than, let's say, some number delta times the initial L2 energy. This is for some delta less than chi. Okay. For simplicity, let me just choose this constant c to be 1, just to go through this proof, right? And normalize the initial L2 norm to be 1. Okay. Now, what was my assumption? My assumption was the h1 norm of theta, the inviscid guy, diverged, right, when I integrate from 0 to t, right? So, okay, fine. No matter how small kappa is, I can find you an epsilon, so that when I integrate 0 to t minus epsilon of h1 norm of theta square, it's at least 1 over 2 kappa, right? So 2 kappa times this is roughly 1. So this blue factor over here in this equation, you can just ignore. That's roughly 1. Okay. So, all right, so what do I have? In that case, difference between theta and theta kappa in L2 is square root of delta. Right? So these 2 guys are small, are close. Delta is roughly the size, right? Now, what else do I have? By my assumption, I said my inviscid guy has a bunch of energy in high frequencies, right? So that was my assumption. So I know the inviscid guy has at least half of its energy in high frequencies. Since the L2 norm, theta and theta kappa are close and delta is small, I can guarantee you that the viscous guy should also have at least maybe a quarter of its energy in high frequencies. Okay. So that's the second one. So now let's tinker with that. And I say, okay, let's look at kappa times the integral 0 to t minus epsilon. Remember, t minus epsilon is what I chose here, right? Of the L2 norm of gradient theta kappa square, right? Integrated 0 to t minus epsilon. Okay, so going from H1 to L2, I can always do the same with this standard trick, right? So I copy the kappa, I pay a price, which is, I know most of my energy is in frequencies higher than n, right? So I just put n square over here and I compute the L2 norm of frequencies higher than n. That's our standard trick, right? But hey, look, L2 norm of energies of frequencies higher than n, I already know this. There's at least, it's at least 1/4. Right? So instead of the second term, I can put 1/16, right? And now if I combine this, the first guy, maybe with a 2 before it was 1. So now it's half. So the whole thing together should be at least 1 over 32, right? So I started out by assuming that the dissipation kappa times integral 0 to t of theta kappa square was small. I said, well, if it was small, it has to be at least 1 over 32. Right? If it's big, of course, there's no problem. So no matter what, you have to have anomalous dissipation. Yeah. Okay. So there's some nice connections to mixing over here. Let me talk about that real quick, right? So what's our criteria for anomalous dissipation? I need one assumption, right, which is I need H1 norm of the Inviscid guy to blow up, right? Then I need some sort of balance, right? So one of the balance assumptions was I need the H1, H minus 1, H1 interpolation inequality to saturate, right? So, okay, H minus 1 decreasing, this is this classical notion of exponentially mixing, right? So if U is exponentially mixing, I know that the L2, the H minus 1 norm after time t decreases exponentially, right? It's like e to the minus some constant t times the initial H1 norm. Okay. How about the H plus 1 norm of theta? Well, this I know, right? I mean, the H1 norm grows at most exponentially, right? So for instance, if U was Lipschitz, I can just Gronwall out and tell you the H1 norm is less than or equal to e raised to norm of gradient UL infinity times t, right? Times the initial H1 norm, right? So in this case, if I write C2 times e raised to little c2t, right, I can choose C2, capital C2 equal to 1, little c2 equals norm gradient u L infinity, right, and get this exponential bound. Of course, you can do better, right? I could choose C2 to be something that's theta dependent. I can pick C1, sorry, I wrote this wrong over here. That should be the exponential guy to be, instead of norm u L infinity, norm u C1, I can put norm u in H1, right? You can do these weak bounds, right? But you pay a price in the prefactor, right? But okay, so let's combine them, right? So I know H minus 1, if I was exponentially decreasing, decays exponentially. H plus 1, right? I know no matter what can at most grow exponentially. But to get the assumption that I stated here, what I really need is matching constants, right? So to clarify, what I really need is that the H minus 1 to decay like e to the minus, I put the c in red over here, so e to the minus c times t, right? And I need the H1 to grow not faster than e to the plus c times t. That's the only way I can saturate this bound, right? I don't know any explicit examples of this, right? In fact, if such explicit examples exist, right, proof actually shows you have enhanced dissipation. So what do I mean by enhanced dissipation? If I look at the L2 norm of the diffusive guy, right? Normally the L2 norm of the diffusive guy decays like e to the minus kappa t, right? But if you have some mixing and you can send energy to high frequencies, of course, this happens much faster. And here's how much faster. Instead of e to the minus kappa t, I have e to the minus t over log of kappa, right? So if I could find a guy here where H minus 1 decays at the same rate that H1 grows, matching constants, right? I get enhanced dissipation with decay like e to the minus t divided by log kappa. And this is, I mean, this is something I spent some time thinking about, right? Because if instead I only had exponential mixing, what I can prove is exactly the same bound, but instead of log kappa in the denominator, log kappa square, right? So this thing, I mean, I really believe that log kappa should be the truth, and I spent some time trying to prove it. I never could, right? This assumption gives it to you, but I don't know how to satisfy this assumption. Yeah. Okay, so here's a sketch of the construction of this example. I was hoping to actually draw it, but let me see. Okay, so hopefully this works out. So here is the sketch of the construction of our example, right? So it's motivated by this Pierre-Humbert flows. What I'm going to do is take a vertical shear flow. Sorry, that's a sawtooth function, which should be the profile of a shear in the vertical direction, right? right? So I'm going to take this, I'm going to smooth out the cap a little bit. That's the epsilon you see over here, right? And then I'm going to alternate it with a shear in the horizontal direction with the same sawtooth profile, right? So I'm going to smooth out the caps a little bit, right? Horizontal shear, right? All right. And then I'm going to increase the frequency. So instead of doing it like this, my next one is going to start going crazy, right? So I'm going to do that as the vertical guy, and then this as the horizontal guy, and then increase even faster every time. Yeah. So that's the picture, but let me just say it a little bit better, right? So here the S epsilons are the okay. So here the S epsilons are the, whoops, it's still drawing. Okay. I don't know if I can. Gianluca, do you see any way for me to stop this annotation? I seem to have clicked it, but okay, it went away. Okay. Sorry. Yeah. So so S epsilon is this smoothed out sawtooth function, right? I'm going to choose a sequence of times tj's that goes to 1. Okay. The difference between these successive times is 1 over 2 to the j. Okay. And then I'm going to choose the frequencies and j's to be 2 raised to alpha j. Alpha is again this level of Holder regularity that I want to preserve. Right. So that's the rate at which my frequencies have to grow. Right. And epsilon is just some smoothing parameter, just ignore it for now. Okay. So what are my shear frequencies, right? Well, between Tj and Tj plus 1, I do the horizontal shear with frequency Nj, which is 2 to the alpha j, right? And then I alternate it for the next time, and then I repeat. Okay? And then we just brute force show explicitly that this saturates the H2 interpolation, right? Namely, so L2, I didn't write the L2 over here because the L2 is conserved, right? So if I look at L2 times the H2, it's bounded above by the H1 square, right? So it's the reverse of the H1 interpolation inequality, and we just show this explicitly by recurrence relations. And now if you add to it our proposition, you get anomalous dissipation with this example. Okay. So let me just say a few things. So now I should clear the annotations. Try. Okay. So let me say a few things about relations to mixing, right? So as before, I'm taking theta to be the inviscid guy, theta kappa to be the diffusive guy, right? If I look at Gronwall's inequality, it immediately tells me that I cannot mix any faster than exponentially. And if you want to be a little bit more precise, what goes inside the exponential? It's e raised to integral in time of the C1 norm of the velocity field. Right? So this is a very quick thing you can do with just Gronwall. Here, norm of theta mix is just some quantification of the mixing scale. For instance, subtract off the mean and take the H minus 1 norm, for instance. Okay. So there's a conjecture of Bressan from 03, which as far as I know is still open. He has a $500 prize, right? Which says the following. Well, I know your Gronwall bound, right? Which is the mixed scale cannot decay faster than the integral, so e raised to minus integral of the C1 norm of u. He's replacing the C1 norm of u in the exponent over here with the W11 norm of u, right? He says that's the lower bound, So if U, instead of being Lipschitz, it's just W11, how fast can you mix? According to Bressan, not faster than exponentially, right? And you need to have the integral of norm U, W11 in the exponent, right? So this is still open as far as I know. If you replace W11 with W1P, then you can do it, right? There's this old paper of Kripa Delalis, right? Some work of Christian Seiss, some work of me, Sasha, and Xiao Shu, right? So, right, but for P equal to 1, it's still open, right? So what happens with diffusion? Well, there's a couple of interesting things that we were tooling around with. So first, with diffusion, instead of looking at H-1 norm, right, I'm going to just restrict looking at L2 norms, right? This is a good enough measure of mixing because, again, right, if I mix really well, I'm going to send energy to high frequencies. As soon as I go to high frequencies, Laplacian works better, right? So I'm going to dissipate energy faster. So just checking how fast the L2 energy dissipates in the presence of diffusion is a good proxy for this, right? So here's one lower bound, right, which I guess is in this, it can be done very quickly, just calculus inequalities. It's in this paper by Poon. It's also really nicely written up in a paper of Charlie Doring and his student Miles, right? So if you look at the L2 norm of the diffusive guy after time t, is bounded below by a double exponential, right? You can't really avoid this double exponential. So initial L2 norm is out front, that's fine, right? And inside the exponent, what do you have? Okay, so there's a prefactor. This prefactor somehow depends on the length scale of the initial data. So it's ratio of L2 and H1 norms, right? And what goes inside the second exponential? Well, it's integral e raised to integral in time of the C1 norm of U, right? So again, C1 norm of U comes, but now it's inside two exponentials, right? So optimality is open, by the way. I don't know how to get anything that's better than this double exponential lower bound, right? But rather than talk about optimality, right, I should mention, if you allow me to do this in the time discrete case, it is optimal, right? I can find examples, but anyway, in the time continuous case, I don't know, right? So here's a question: what bound do you get, right, if instead of putting the C1 norm of U in the exponent, I do something weaker, right? Put a W1P norm instead of W1 infinity, right? So here's our conjecture, right? So I'm going to take the lower bound that we have, right, from Poon or from Miles and Doring, right? It was actually shown to me by Sasha, right? So let's take this lower bound. Instead of kappa up there, I'm going to replace it with R of kappa, some rate, which I'll talk about in a minute, right? And instead of the C1 norm of the velocity field, I'm going to replace it with something weaker. Let's take the W11 norm of U, right? So R of kappa is some function that vanishes with kappa. Initially, actually, we wrote this with R of kappa equal to kappa, and Bru and Nguyen pointed out this isn't possible, right? So we owe them thanks, right? So just a quick observation: if I look at this conjecture for the lower bound and I add to it the energy inequality, right? This implies an upper bound for kappa times the integral 0 to t of norm gradient theta square, right? Sorry, let me correct myself, norm gradient theta kappa square, right? This is my anomalous dissipation guy, which I just spent some time talking about, right? So what do we get on the right-hand side? It's initial L2 norm 1 minus whatever this double exponential is, right? So let me pick little t equal to capital T to be something of order 1 and fix it. Let me pick kappa really, really small, okay? So what does this imply? That kappa times the integral of the H1 norm of theta kappa square is bounded about by your initial L2 norm, and then this entire thing over here just becomes R of kappa, same order of magnitude, right? So consequently, this conjecture is certainly false if I replace norm of gradient U L1 with norm of U in C alpha. So going below W11 is not going to work out because, well, I have this anomalous dissipation example, all right? I mean, in the example we had, U was C alpha, and this guy here was order 1, right? Not vanishing, okay? So there's this recent work of Brew and Min, which suggests R of kappa should be 1 over log kappa. There's some work also by Christian Zeiss, right? Let me not go in that direction. Also, I don't know what to do if I put any LP. It doesn't have to be L1, right? And loss of regularity for this transport equation makes things hard, right? When you're working with these rough velocity fields. Yeah. So let me stop there. Here are some references. Thanks, and sorry for the technical issues. All right.
Thank you, Gautam. So that was very nice. Maybe I try to get again my screen to see whether there are questions.
Hey, Gautam, I have a question.
Hey.
So if you can go back to the slides with the criterion, with where you saturate the inequality, the interpolation inequality, or I don't remember what number.
I'm attempting to go back.
No, yeah. So you see, here you say that if you were for, and I think it's already a very hard question, get exactly the same little c in the red c that you have there, right? But you're still having a problem with the norm on the initial datum as well. Am I correct? Because there you have theta 0 and H1, and then you will have like the theta 0 and H1 squared is less than or equal theta 0 and L2 squared.
Yeah, but that's okay. That's a constant that's independent of time and independent of kappa, so fine. Some constant that'll show up, fine, right?
Yes, but I mean, I would say that in the enhanced dissipation rate, you will get the rate.
Yes,
I mean,
you're absolutely right. So this would show up in the enhanced dissipation rate. You would have, you're right, there's a mismatch of norms. So the chi would depend on theta 0, right?
Mm-hmm.
So, but you would still have anomalous dissipation with some rate that depended on theta 0, and that's fine.
Because my feeling is that you can never propagate that because the H1 norm you can control very well. Is that right? I mean, I've always got confused about this, so I'm asking.
Yes, propagating, that's a different business. Yeah, I don't know.
Okay.
Right.
Okay, thank you.
I had a question on the same point. Sorry, Gautam. I would like to understand better how restrictive is this condition, this extra condition on the saturation of the interpolation inequality. In the sense, I mean, how should one imagine it? Like I was trying to interpret it in terms of Fourier coefficients, and it seems to say that the function have to be localized around certain Fourier coefficients, but maybe you have a better interpretation. And maybe can you give more details even on why in your explicit example you can get some condition of this type?
Well, okay, so this is so as in why we get this condition, right? So we just do recurrence relations and solve it, and it's a bit of a mess. Okay, I don't know if I want to go there, right? In terms of what this condition means philosophically, I really should have a better way to say it. I don't. You're right. I really should have found a better way to say this, and I don't have one right now, because it's somewhat striking to me. Because I'm basically at any level, if you just saturate these interpolation inequalities, it works. You have anomalous dissipation. right? Yeah, so I don't have a better way to say it than saturating the inequalities, but let me think and get back to you.
Maybe you should go back to no, I'm just suggesting something to address this issue. Think about random lacunary series, so you get saturation this way.
That's a good point. Right.
So my only comment regarding your question earlier this morning. So these are linear equations, and in some sense, linear equations are both harder and easier than nonlinear equations. In nonlinear equations, you might hope for better results, which is, from some perspective, worse results, meaning that you don't know to get lower bounds as easily because you cannot control the nastiness.
Yes, indeed.
Yeah. But yeah. So.
So, Michele, you have a question too, or?
Yeah, I'd probably kind of a technical question, but I'm wondering if the time scale on which you alternate the shear flow does depend on the coefficient kappa that you're going to send to 0.
No, because the flow is chosen independent of kappa. Right? It's just one velocity field for all kappa. So the time steps are chosen. It depends on the alpha, right? But right.
Okay, thanks.
Yeah. I also have two small questions. So one is exactly on this slide, so this slide 11. So here it seems to me to suggest that you have propagation of regularity for the solution if you have some h1 bound on the velocity. So I'm slightly puzzled by this last part of this item because.
Right. So I guess let me respond with a question. How does the highlighting work so well when you do it and not when I do it? But okay, you highlighted exactly what you wanted to show.
So you have a Mac, so and I know you're late to me now.
But yeah, so all I meant by okay, maybe better was a bad word, but maybe more realistic, right? Because if I look at the initial bound, if I just choose U to be Lipschitz, right? The bound that you get out of Grunwalling this is really a worst case bound. E raised to norm U C1 times T. That's worst case. It doesn't happen, right? Well, okay, maybe it does, but it's right. We need to do a lot better, right? So in that sense, I was trying to say, okay, if I put instead of C1, right? If you think about the C1, I mean, this exponential growth, I mean, maybe it happens at some points, but not everywhere. And if you measure like H1 norm of theta, right, you shouldn't overly penalize those. So that's why I was trying to say, okay, if instead of putting C1, you put U in H1, right? You can still get a bound. You put the H1 norm in the exponent, but I mean, of course, it's still not good enough. You pay a prefactor. Is it more realistic? I don't know, right? The thing I really need is something with matching constants, and I have no examples of this, right? I guess to point out one of the questions earlier, right? Even for the flows that we construct, right? We cannot tell you that that you have matching H-1 decay to H+1 growth. We can't do this. We saturate the H1 and H2, but here I don't know what to do.
So you mean this as an assumption on some specific case? You don't mean as a universal bound, which okay, that
yes,
works.
Yes, absolutely.
Okay,
absolutely.
Okay.
So just one thing about this. I know that maybe it's too simple, but if you take the Coherent flow and you don't want to prove, of course, log k timescale, but k to the 1/3, you can get matching bounds. or they're 1 over t and t instead of exponential. So, I mean, because h minus 1 decays like 1 over t, h1 grows like t. So, I mean, any monotone shear flow will do, but if you just want to be as explicit as possible, you can get that. Although you still have this problem of not being able to propagate the band, but you do, I mean, that's the only example I know in which you have matching bands. But of course, it only will give you some, you know, k to the 1/3 enhanced dissipation. I mean, that's one of the way to prove enhanced dissipation in this case.
That's no, that's actually a good point, right? I didn't realize that you have these saturated bounds for the Coherent flow, but maybe we can chat, right? I don't know if we can get anything out of this or not, but it's certainly worth talking about, right? Maybe we can chat a bit later.
Yeah, of course, of course.
I would have another question when you were mentioning your example of non-uniqueness or the corollary to the non-uniqueness. Maybe I go up to that. So do you have a passage to subsequences here when you use Aubin-Lyon? Because what I was wondering is, so it's very, you know, especially, I mean, I like it. It's very strange that the vanishing viscosity does not select the reversible solution. I was wondering if for your example, in a sense, you are selecting another well-defined notion of solution in a sense by vanishing viscosity, which is different from the one from the renormalized one, for instance. So you have two canonical solutions in the limit, renormalized and vanishing viscosity. Maybe on this example, does it make any sense to you?
No, this is an excellent point, which I really should have thought about earlier, but you're absolutely right. Am I guaranteed that the vanishing viscosity solution here is unique, is basically what you're asking, right?
Yes.
I mean, that's a great question. I really should have thought about this, and I did not. Of course, I can't tell you now because I don't know, but I should think about this. Right.
It's not clear from you. Okay. Because it's small, because you asked something to me before, so about this, so whether this abstract existence proof, I don't know whether I would call it abstract, because in a sense, what we do is we characterize vector fields for which we have uniqueness by a strange condition, which is this sort of SARD, but then we give example, I mean, rather explicit example of vector fields which do not satisfy that condition. So I don't know whether I would call it abstract, but that's very minor. I mean, it's
sure,
just the wording, of course, yeah.
Right, but it's one of these generic criteria that you have, right? You say almost everything should, right?
No, I don't think we have a bear, so I think it's either a recursive construction. No, I don't think we have any bear category in the construction. So I think we have bear category argument at some point when we show that, you know, generically, that condition for the uniqueness is satisfied, but not for the counterexample. As I remember, it's a few years back.
I see. So, okay, I should really correct myself when I quote you here. Thank you.
But
yeah.
That's not.
Right.
So any more questions? Seems not, so it's already quite late in the evening here. Okay, so I thank you, Gautam, very much, and all the speakers of today. So just as a reminder, so we resume tomorrow, while European time at 10 a.m., which I think is quite prohibitive for the colleagues from the US. And there will be recordings available online of the talks of today and you know, after tomorrow morning session of the talks of tomorrow. Okay, so thanks everybody, and see you tomorrow.